Hey everybody, welcome to our tutorial on unbiased learning to rank, counterfactual and online approaches. We're a team of three, Harrie, Rolf and Maarten. There we are. So Harrie, you may want to share your voice with us for a second.
Hello, I hope I look like my picture.
Rolf?
Yeah, hi everyone.
All right, so we're all based at the University of Amsterdam. Harrie and Rolf are PhD students. I'm a professor, and we're thrilled to be able to take you through our tutorial on unbiased learning to rank. So what we have in mind is the following. Hopefully by the end of this tutorial, you should be convinced of how important it is to learn to rank from interactions with users. We hope that you understand the most relevant algorithms in this space, both in counterfactual learning to rank and in online learning to rank. Ideally, you're also capable of deciding what type of learning to rank from user interactions you should use, in which cases. And hopefully at the end of this, you'll also be inspired to contribute further development of methods for learning to rank from user interactions. Now, this is our plan. It's a colorful plan. It's a tutorial in 4 parts, a brief introduction, then a long chunk on counterfactual learning to rank, another big part on online learning to rank, and then finally a conclusion where we both wrap up and compare and try to look forward. Now, when this tutorial is being broadcast at the conference, we'd like you to share any questions that you might have. And so we suggest that you use Twitter for this. Our handles are here for Harrie, Rolf, and myself. And if you use the hashtag LTR tutorial, we should be able to pick up your questions and hopefully respond to them with answers that, that help you. Also, what we'd like to do is, at a later stage, once we've collected all of the questions, produce a follow-up video and also share that with you. Okay. Part 1, the introduction. What we'll do here is we'll look at supervised learning to rank methods that use annotations, that need annotations. We'll look at limitations of these methods, and we'll talk about learning instead of learning from annotated datasets to learn from user interactions. And then we'll talk about noise and bias as 2 really important factors to consider. So in learning to rank, if we quote an influential tutorial and survey written about 10 years ago, learn to rank is the task of automatically constructing a ranking model using training data such that the model can sort new objects according to their degrees of relevance, preference, or importance. Learning to rank is a core task in many areas in information retrieval, in search, where you would rank, say, suggested queries or documents, in recommendations, where you might rank individual items for people to consume, or baskets of items, or sequences of items, and in digital assistants, where you might rank responses or even types of response. So should we prefer a textual response or a visual response, or should we opt out altogether if we're not sure about the top ranked results?
So we're going to use some mathematical notations later on. And the way we're going to use them is that we'll have a ranker function, which is f theta, as you can see here, and which is going to rank or over a document set. So document set D, so this D the set will have a lot of documents which will be ranked. These can be items or products or videos, you name it, but we're going to call them documents because that's the traditional learning to rank setting. And we'll call R a ranking, which is just the sorted set or the ranked set of documents according to this model. So the model will decide what the ordering is. So R is just an ordered set where R1, R2, R3 are all documents at different ranks. And we're going to sort them according to their descending scores. There's no real reason for this. We can, ascending or descending, it's completely arbitrary. But for this tutorial, we'll stick to descending just to be consistent and to make everything clear. And finally, a small detail, but every document has to be in the ranking. So when we rank something, we're not selecting, we're only determining the ordering. All right. And there we go. So we're going to cast the problem here, the goal for our learning to rank, to find the parameters, which we call theta, for this model. And we want to find the parameters so that if we sort according to the scores, as you saw on the previous slide, we get the most optimal rankings, right? So the parameters so that the model orders the documents in the way that we want it. There's of course the question, what is optimal exactly? We'll get to that later. For now, this is as specific as we'll be. And before we get into how you do this from learning from user interactions, we're going to talk about the classical way of doing it, which is supervised learning to rank. Now, these methods are based on annotated data sets. And such data sets usually contain examples of queries that users usually use or have used or will use, documents, the thing that we're going to rank. And usually there's a pre-selected set of documents per query. Usually there's some system that determined the top 1000, for instance, and relevance labels. So for each combination of a document and a query, we need to know how relevant is it or how preferred is it, which is the signal that we want to learn from or evaluate on. And then commonly, these methods are divided in 3 groups: pointwise, pairwise, or listwise methods. If you know anything about learning to rank, you've probably heard of these before. We're going to go through them very quickly just to set the stage for the rest of the tutorial. But first, a little bit about these annotations. So these relevance labels, they have to be gathered by human judges or human annotators. So that means that people were shown these combination of documents and queries and asked, does this look relevant? Does this look good or not? And these are really nice because we can use them as supervision, right? We have something that we can consider a gold standard. What we're going to do in our notation is we're going to use this YD as the relevance function. So this will tell us what the label is that we gathered with through human annotation. So YD will just tell us if something is relevant or not, or how relevant. Another thing is we're going to use a notation where we just say D instead of document and query, because we're never going to talk about multiple queries in the same contents. Whenever we're ranking documents, there's usually a single query. Just to keep things brief, we'll just use this notation. But it should always be clear what query we're talking about just from the context. All right. The first set of approaches is the pointwise approach. And the pointwise approach really isn't a learning to rank method, as in this is sort of the standard machine learning way of approaching the ranking task through classification or regression. And for instance, as you can see here on the slide, you can use the mean squared error, right? You can have your prediction of your model coming out of, so this f theta, be the same as your relevance function, or as close as according to this mean squared error, where you're trying to match your scores of your model with your relevance labels. Just common regression. Now, of course, this is nothing different than you see in other machine learning fields. So it's it's not really, so if it just came down to this, if this worked very well, we wouldn't need a separate field of learning to rank. But it doesn't, right? That's why we're here today. The issue with this approach is, with these pointwise methods, is that they ignore the core characteristic of the ranking problem, and that's that these model scores are used to rank documents. To put that in a different language, a pointwise loss or regression loss or classification loss only wants these scores to be close to the labels, right? It wants these, if something has a score of 1, it wants the score of them all to be close to 1. But for ranking, we don't really care about the exact value of the scores, we care about the ordering. If you see a ranking, you don't know what scores produce that ranking, you just see the ordering in which it's displayed to you. So it's the only thing that matters. And what happens is that these pointwise methods compromise the ordering to get scores closer to the labels. So to produce scores that are closer to the actual relevance labels, they sometimes worsen the ordering. And that's not what we want, right? Because ordering is exactly the thing that we're interested in. So as a solution, the first set of what we could call the first real learning to rank approach was the pairwise approach, where they realized that this scoring, the ranking is based on relative score differences, or ordering is based on relative score difference. So you can construct a loss over pairs of documents where there's a difference in relevance. Now you can see this method is almost 20 years old, but it's very straightforward. We see here a pairwise hinge loss. And the basic idea here is that we sum over all the pairs where one document is more relevant than another document. And then this hinge loss over here is going to push the score of the relevant document to be greater than the less relevant document. And if that difference is greater than 1, then this operation, this max operation will turn into a hinge loss where you don't optimize it anymore. But it pushes these documents away from each other if there's a relevance difference. So the scores don't have to match the labels, they just have to be in the right ordering. So the first real learning to rank method. The problem with this approach, though, is that it treats every document pair as equally important. In practice, when we actually use ranking systems in search or recommendation settings, or really any setting usually, we care more about the top 10 than the top 100. So it's more important when you're searching for something on the web, for instance, that your answer is in the top 10 results and not in the top 100, because usually we don't go that far down the list. Of course, there's contexts where this might be different. The problem here is that the pairwise method doesn't look at the pairs that it's trying to fix, where they are in the ranking. So what happens is that these methods sometimes compromise the quality of the top 10 to improve something in the tail of, for instance, the top 100. So it's improving the ranking very far down the list, but decreasing it right at the top, where it matters the most. So another set of methods was required, and this came in the form of listwise methods. These methods try to optimize ranking metrics directly. So for instance, if we care about DCG, as you can see the formula here, famous ranking metric, we want to optimize that metric directly. Because if the metric is tells us what the quality is, then that's what we should be optimizing as directly as possible. The problem here, of course, is that this isn't differentiable. In particular, this ranking function is something that we can't just differentiate. So we can't use something simple like stochastic gradient descent. These listwise methods, because of this, they are mainly look to solutions to this problem of how do you optimize these discrete ranking functions. And there's several ways. There's a probabilistic approximations like listnet. We also have heuristics or bounds like the famous lambda rank or lambda mart or later lambda loss. For instance, here we see the lambda rank loss where we also sum over these pairs, but now there's a weight according to how much the DCG changes when you switch a pair. I'm not going to go into more detail here. In the counterfactual learning to rank part, we'll see some more examples. All right, then I'll give the slides back to you.
All right, thank you, Harrie. Right, so now that we've had this extremely brief overview of learning to rank from annotated datasets, let's take a step back and think about what some of the limitations are of learning to rank from the annotated datasets. So, of course, we need people, we need human judges to create these query document pairs that provide the relevance annotations. And over the years, the research community has come up, has bumped into, as maybe a better way of phrasing it, into a number of limitations of this approach. And an early one is super obvious. You know, that you need quite a bit of data to train effective learn to rank datasets, learn to rank methods from annotated datasets, and that's expensive. In some cases, it's just not appropriate or not even ethical to collect such data. Think, for instance, of highly sensitive, highly privacy-sensitive settings. Could be in email search, could be in medical search, where it's just not appropriate to have judges generate annotations. In other cases, it might be impossible. Think, for instance, in personalized search of your personal document collections on your laptop or mobile phone. There's probably only one judge who can provide suitable annotations there, and that's you, the owner of this data. Another interesting phenomena that has been looked at from a number of angles in the past couple of years is the fact that relevancy is usually not a stable feature. Things that may be relevant now need not be relevant tomorrow, and things that are not relevant now might become relevant later on. Think of big events, big news events, where instead of a big news event, for instance, at a particular location on the planet, instead of giving the usual Wikipedia page as a background document for that location, now because of the news event in that location, you would need to return news documents, the latest facts at the top of the ranking. Now those are more relevant than the general background information. So it's not stationary, and of course annotated datasets would be stationary. They would have fixed annotations per document for a given query. But potentially an even bigger challenge is the fact that these annotations provided by judges don't necessarily align with what actual users want. Annotators and users disagree, and that's a big challenge. And so one of the motivations certainly for learning to rank from user interactions is to, in a sense, get the signal closer from actual users, who will be the people consuming the ranked lists of documents that we generate. And so they're valuable, these annotated data sets. They're extremely valuable. They help us in research, in innovation, in development. But you need a considerable budget to create them. You may not always be able to create them. And even if you are able to create them, then they may not be the right material to learn from, because they may be misaligned with the actual user preferences. So let's think about an alternative. Let's think about a way of informing learning to rank methods, not from annotated data sets. And for this, we're going to look at counterfactual learning to rank. So back to you, Harrie.
Thanks. All right, welcome back. We're now presenting, we're going to present the second part of the tutorial on counterfactual learning to rank. For this part, it will just be me and Rolf, and we'll be discussing first counterfactual evaluation, Rolf is going to talk about that, how to evaluate unbiasedly from historical interactions. Then I will take over to talk about propensity-weighted learning to rank, so what we call counterfactual learning to rank. And then we'll talk about the remaining topics together, which are estimating position bias, some practical considerations if you're going to use these methods in the real world, and some related work. We're going to compare this with click models so that you understand the difference between counterfactual evaluation and the existing click model work. All right, Rolf, if you can take us through the next section.
Yes, thanks, Harrie. All right, so I'm going to start off by talking a bit about counterfactual evaluation, which is really about evaluating a ranker before you want to deploy it. So evaluation is incredibly important because we do not want to deploy a ranker to real users when that ranker is not well performing. That would degrade the user experience. But as we have seen in the introduction, there are limitations of using annotated data sets. So the question we're mostly interested here in this counterfactual evaluation part is, with these limitations of annotated data sets, can we evaluate a ranker without actually deploying it and without having access to annotated data? That's sort of the key question we're interested in here. So this is essentially counterfactual evaluation, right? And to put it a bit more formally, we want to evaluate some new ranking function. We call it f theta, using historical interaction data, for example, clicks. And these clicks were collected from a previously deployed ranking function, which we'll call fdeploy. All right, so before we go into that whole counterfactual evaluation and how we solve that, we're first going to talk a little bit about just regular evaluation of rankers, specifically something we call full information. And this is if we would know the true relevance labels of documents. So what we have here is this YDI, which stands for the relevance of a document DI, and we know this for all I. We're going to just assume that for now we know this. And this is the typical case when you have annotated data sets. You know exactly how relevant each document is. If we know these true relevance labels, then we can compute any additive linearly decomposable IR metric as the following formula, where we write this as delta with three parameters: the ranker that we wish to evaluate, that's f theta, some collection of documents, and this relevance labeling function y that gives us the relevance labels. And then we can write it in this form where we have this lambda function, which I'll talk a bit more about later, and we have this rank function here. And this thing tells us what's the rank of a certain document DI after we sort all the documents by our scoring function f theta. And then finally, we multiply all of this with our relevance labels. So to show you that this is valid for many IR metrics, here we have some examples for this lambda, this rank weighting function. For example, when you just take the identity function, you get out of this formula essentially the average relevant position. So it's just computing the average relevant rank of documents. But you can also compute other IR metrics. For example, DCG, by plugging in this form of lambda, 1 over the log of 1 plus r, where r is again that rank of that document after sorting by those scores, we would get DCG out of this. So this is sort of a general phrasing of certain IR metrics that we can use. Of course, the key component here is that we know these true relevance labels. We have this labeling function y that tells us what's the relevance label for a given document. So to give you an illustration of this, here we have, say, 5 documents, document D1, D2, D3, D4, D5 in that particular order. And we know that by our relevance labeling function, documents 1 and 4 are the relevant ones, and documents 2, 3, and 5 are not relevant. And then we can plug in the previous formula, this one with these different lambda functions, to get different metrics out of that. So we can literally compute for this particular ranking, what's the DCG, what's the average relevant position, etc. Right? Of course, again, the drawback is that we need to know the true relevance labels. We need to know this why. So in practice, we often don't know the true relevance labels why, right? And as we have seen before, you know, there's limitations to these annotated data sets. But what we can do is we can observe implicit feedback, usually in the form of clicks. So what we have there is that we have a click, CI, we'll indicate that with CI, on a particular document, DI, and a click is typically a biased and noisy indicator that document DI is relevant. And importantly, if a click is missing, that does not necessarily indicate that that document was not relevant. So to give you an illustration of this, we're gonna go through a typical user process that goes through a ranking of documents. So we have a user comes into the same ranking list that we've shown before. Again, we know for now that documents 1 and 4 are relevant, but we'll see how a user perceives this. So a user comes in, the user looks at the first document and decides, oh, that's relevant, and clicks on it. So we get a click for the first document, right? Mm-hmm. Then the user comes back to the search session and moves on to the second document. The user looks at that document and decides, oh, that's not relevant, I'm not gonna click on it, right? Then a user maybe continues to document 3. The user looks at it again, and for some reason, maybe noise, maybe some other reason, the user does decide to click on it. So we do get a click on document 3 for some reason. At this moment, the user may say, oh, I've had enough, I'm going to do something else, and sort of quits the search session. So the user will not observe document D4, and as a result, they will never click on it. And the user will also not observe document D5, and as a result, also not click on it. So the main thing we see here is that we have our relevance labels on the left side, which indicate that document 1 and document 4 are relevant. And we have our clicks on the right side, which tell us that, you know, document 1 and 3 are clicked. And obviously this is a mismatch, right? This does not align with these relevance labels that we have. And that's purely because of the behavior of users. So the reason we are seeing this, there's many reasons for this type of behavior. And there are many reasons why a click on a certain document in a ranking may not occur. So first reason would be relevance, right? Document may simply not be relevant. As we saw in the previous example, document 2 was not relevant, the user did not click on it. Another important property as to why a click may not occur is observance. So as we saw, the user never looked at documents 4 and 5, and as a result didn't click on them, even though document 4 was relevant, right? And there might be other random reasons why a user may not click, because of noise, because of some other random reasons. So we can broadly classify these reasons into either being caused by noise or being caused by bias. And in the first case, when it's noise, someone just happens to, with some random probability, click or not click on a certain document. If we have many clicks collected, we can typically average and then sort of cancel out that effect. So basically, as long as there is, you know, more probability of clicking on a relevant document than a non-relevant one, then you can just average large numbers and infer some preference there. The real problem lies in bias, where averaging will not remove that effect. So we'll look now more into that.
Can I ask you about that?
Yeah,
so,
sure.
You're saying clicks are related to relevance, right? So it's not as if clicks are clearly somewhat dependent on relevance. But because they're biased, you cannot just, if you have a large number of clicks, if you have a really huge number of interaction data, like an average click-through rate will not give you the relevance still.
Right, that's correct, yeah. And the reason is that some forms of bias are sort of a consistent effect on how you're collecting your clicks, essentially. Like you can imagine if you put a document on, say, rank 100, like very deep down into the ranking, you're never gonna get a click on it, even though it might be a relevant document. Whereas a document that appears at the top of the ranking might get a lot of clicks. And this is a phenomenon typically called position bias, where the position of the document matters.
Yep.
And even if you have a lot of clicks, you're still not going to get a lot of clicks on position 100. Right?
So there's no simple solution. I can't say, okay, I'm just going to collect 10 years of data and then my averages will be right.
Exactly, yeah. Even if you average over huge amounts of data or even infinite data, you will still get the wrong answer.
All right.
That's correct, yeah. All right, so what we've essentially just seen is the way users behave, right? The way a user might behave when they browse a ranked document list and they decide to click or not click on certain things, right? So we can try to formalize this a bit more, which is important for the counterfactual evaluation. And we're going to formalize this in the form of an examination user model. And we're going to do this to sort of build assumptions of how a user behaves when they browse ranked lists. This is by no means the best model or the only model by which you can assume user behavior happens, but this is a very common model that is commonly used. And the way we're going to do this is we're going to say a user click is only going to basically depend on whether a user examines a document and whether they judge it as relevant or not. Okay. So we have examination and relevance, and then we can model a user click as follows. So first, we're going to define some probability of a document being examined. We'll indicate this with this OI notation. So whether a particular document was at all observed in a particular ranking R. So we're going to write that with this probability statement here. Probability of OI equals 1, conditioned on the ranking and the document. Then we have the second probability, which is the probability of a click. And the probability of a user clicking on the document is conditioned on whether that document is relevant. So intuitively, you might think, oh, a relevant document should get more clicks. But it's also conditioned on whether that document was observed or not. So it's conditioned on that variable as well. And then the main assumption we're making in this examination user model is that clicks can only occur on examined documents. And basically what this implies is that we can write the probability of a click in a certain ranking of documents as follows. So we have the probability of a of CI equals 1, so a click, and this document being observed, OI equals 1, is conditioned on the relevance and the ranking that was displayed in. And we can write this or decompose this into these two probabilities. The first being the click probability given that this document has been examined. And the second probability is the probability of it being examined at all. So that's sort of how we're decomposing this probability. And this is just, again, one of many user models that you could have for examination.
Right. So here you have some assumptions here, right? So you you first assume that examination or observation only depends on depends on the ranking, but relevance only depends on the document.
Right. That's correct. Yeah.
And you're saying if we see a click, then we're going to assume that someone must have examined that link. Like people are not clicking without looking at something first.
Right, that's correct.
Vice versa, right? If someone is not looking at something, they're also not going to click on it.
That is correct, yeah. These are just assumptions, again, built into this model. Whether these are valid assumptions depends on what type of ranking application, of course, you have. For like a typical web search scenario, these are, I'd argue, pretty reasonable assumptions, but there are, of course, other cases that you can think of where maybe these are not good assumptions. So you always need to be critical of how will we model the user behavior and how do we model these clicks, essentially. This is a very important part,
But it seems very fair. I mean,
Sure. Cool. So we've now seen sort of, okay, how users behave, right? How users click on documents. And we made some formalizations here, some assumptions on user behavior. So what we can now do is we can think about this evaluation measure that we had before, right? This delta function. And we can just very naively use the following approach. We can just say, oh, if someone clicks on it, it's relevant, and if someone doesn't click on the document, it's not relevant. Under the models that I've just shown you, that user examination model, that's obviously not the case. But if we assume naively that that gives us an unbiased relevance signal, the clicks, then we can have this estimator here, this delta naive. And this will work again for any of these lambda functions or any IR metric that we can express like that. We can then measure like this. Now, of course, the problem with this is exactly the assumptions we've just made. So if we assume that users behave according to that examination user model, then this estimator will give us a wrong answer. So we're going to show this right here, right now. So here we're going to say, even if there is no click noise at all, right? So if a document is relevant and it was observed by the user or examined by the user, then a user will always click on it. And if a document is not relevant and it was observed by the user, then there will be no click on it, essentially. If we assume that, so there's no noise at all, then this estimator that we have here is still biased, and it's biased by these examination probabilities that we have from our user model. And to show you this, we're going to just plug in this estimator, this delta naive, into this expectation. And then we're just going to work out the equation. So we first plug in essentially this formula, this sum over the documents of this lambda times the clicks. We just plug that in our expectation here. We are rewriting the sum here a little bit. So instead of saying times CI, we are essentially saying, well, click only occurs if a document is observed and it's judged relevant. So this is both that examination user assumption and the fact that there's no click noise, right? So we're assuming both of those things here. Then we can rewrite the sum in this form, and then we can work out this expectation, and this expectation over the observation probabilities. If we do that, then what we get back here is a sum of the following form, where we have a sum over documents where these documents are relevant, times, so then for each document we have the weighted rank of that document, so that's good, that's in the end what we want. But we have this extra term, this probability, this examination probability. And that's the thing that's biasing this estimate. So ideally, we want to not have this examination probability in this equation. Then we would have an unbiased estimator. But clearly, this probability happens because we're assuming that users behave in that particular way.
Right, so you're also working with binary relevance here, right?
That is correct. Yeah, I should clarify that. So clicks here are either, or relevance is either 1 or 0. So either a document is relevant or it's not relevant.
I think we mentioned it in the first part, but
right.
it's good to repeat. Yes.
Yes. Yeah. So this y function is 1 or 0 essentially. Yeah. And under the click noise setting, of course, that would mean that a click is perfectly reflecting that relevance. But we still have this bias problem because of these examination probabilities. So yeah, moving on, what does this intuitively mean, really, right? So this estimator is biased, and what it's intuitively doing, it's weighing documents according to their examination probability in the ranking R displayed during logging. So again, repeating this formula, in expectation, this estimator is going to give us is the thing that we're interested in, but multiplied by this examination probability, this extra sort of weight factor, if you will. So documents that are more likely to be observed are sort of intuitively given more weight for our evaluation in the end. And what this results in is that, particularly for rankings, we say that documents at a higher rank are more likely to be examined, and this is a phenomenon called position bias. So again, going back to that web search ranking example, a document that sits at the top of the ranking versus a document at position 100, obviously the one at the top of the ranking is going to be examined much more frequently than the one at the bottom, because people don't go that deep into a ranking, typically. So when you have this position bias phenomena, what this estimator is going to do is going to cause what's called logging policy confirming behavior. So documents that were displayed at higher ranks during logging are incorrectly considered as more relevant because they are getting more clicks, because they are examined more often. So you're not fairly comparing documents really here. So a document that just happens to be positioned lower is incorrectly considered as less relevant.
Right.
Purely because of its position and not because of its relevance. And this is the core problem with using such a naive estimator.
So this is the core problem with naively using clicks, right?
Yes,
it's
correct.
a good idea if we quickly summarize it again. So on the previous slide, you showed us this formula on top, right? So if you were to just use the clicks and say, oh, the clicks will indicate relevance, maybe with some noise, but averaging over a lot of data. And now what you've shown here is that if you calculate sort of what do we expect this to converge on, like an expectation, what we would get out of this, it is not what we were looking at before, right? Before we were looking at relevant times this lambda function.
If I quickly go back to that, we have this function that we're interested in.
Yes.
We want our expectation to essentially become this function.
This is what we want to get out of it, yes.
This is what we want to get. But as I've shown you in that formula, there's this extra probability inserted there. So it's not the same thing as if we were to know the true relevance labels.
Right.
So
can you go to slide 26 again?
Sure.
Right. Yes, yeah. So we have this probability of examination in the way that's reweighing them. And you're saying these probabilities are caused by the way that we were logging the data. So when we were gathering the data, where did we show this document? Right. Yes. Okay.
Right. That's correct. And this is important as well. This is what happens during logging. So it's actually the deployed ranker that was collecting all of these clicks that is sort of influencing this bias. Yes. And that's also why we get this logging policy confirming behavior, because whatever our ranker was doing at the time of collecting clicks, we are sort of incorrectly considering that to be the best way to do things, essentially, right? Because it's going to put documents at high rank, so we think, oh, that's good to do because that gets a lot of clicks. Right?
So if we were to base learning on this, you would expect that the documents that are on the higher ranks during logging have a sort of an unfair advantage.
Exactly.
They're going to be all right. It's actually a good rule of thumb, I think. If you can see that in expectation, the way you were logging data is affecting the place that you converge at, it's a bad signal, right? Because what is a good ranking shouldn't depend on the way that you were logging data. So we can clearly see that this is not going to work. Yeah. All right. Yeah, I'm excited to see how we're going to fix this.
Yes, exactly. So I mean, the core problem really is this. This examination probability that suddenly got introduced there just because of the way users behave and because of what documents we happen to show at certain ranks. So we're going to now move on to the next part, which is about something called inverse propensity scoring. And instead of taking this naive estimator that we have here, we're going to introduce a new estimator that hopefully is going to get rid of this examination probability. That's our end goal, if you will. So this is called inverse propensity scoring. And this is sort of the core part of counterfactual evaluation. And it is getting rid of this bias that we just saw got introduced by using this principle of inverse propensity scoring. So I'm going to jump right into this formula here. We have, again, this delta function, which is our evaluator or estimator for our evaluation. And this one looks pretty much the same as what we had before. It's also taking clicks, so we're just assuming that clicks are sort of a proxy for relevance, like we have here, the CI. We have the same lambda weighted rank at the top, but we have this new term where we're dividing by this examination probability, if you will. So this is the only really new thing that we introduce compared to the naive estimator that we had before. We're just dividing by this examination probability. So again, to reiterate this formula, first we have this lambda rank. This is the weighted rank of a document, DI, after it has been ranked by F theta. So it's all these documents in capital D have been scored by F theta, and then what is the rank of our document DI? And then apply this lambda function to weight that rank to get different IR metrics. CI is, again, the observed click of that document in our click log, in our historical click log. And then this probability here that we have at the bottom is the examination probability of this document DI in this particular ranking R displayed during logging. So what was the probability that that clicked document DI was actually observed? And our claim here is that this is an unbiased estimate of any additive, linearly decomposable IR metric. This is what we claim.
All right, yeah. So before you, because I know you're about to prove it, but just to be clear, what's happening here is, so the new ranker is this F theta, or the ranker that we want to evaluate.
Correct.
But R is the ranking that was displayed when this click was logged, right? So in the division, you're correcting for what was happening during logging in the denominator. And in the denominator, you have the new value for your new ranker.
Correct.
And it looks like the less chance you have of being observed during logging, the higher that you're being weighed, right?
Exactly. That's sort of also the intuition behind this, because if you put a document in a place like very low down the ranking where it doesn't have much chance of it being observed, the one time that it did, or the few times that it did get observed and get clicked, we should probably count that more heavily than a document that was at the top of the ranking, because that one got observed a lot of times, right? So we're sort of, reweighing according to that inverse propensity score, essentially.
All right.
Yeah, and it is important that that is the observation probability during logging. So when you are collecting the data. It's a good point.
Yeah.
All right, so I'm gonna, the next slide will, I think, have a lot of math. So don't be scared. So this is essentially the proof that that estimator we just had is indeed unbiased. And I'm gonna walk through this line by line. It's actually a fairly clean elementary proof, I think. I think it's one of these nice results from IPS that you just sort of get.
Easy for us to say, of course.
So what we're going to do here is we're just going to assume there's no click noise. Again, similar to what we've done before. So we're going to say that if a document is relevant and it was observed by the user, then they'll always click on it. If not, the user did not click on it. That's the main assumption here. And we're going to do the same thing. We're going to start off with our estimator, and we're going to try to take the expectation of this. So for what this converges to, if you have a lot of clicks, essentially. So we just plug in the definition of our IPS estimator. So the one that we just introduced here in the previous slide. We're going to just plug in that definition right here. That's all we do. And then we can rewrite this sum in a little bit by our assumption of not having click noise and our examination user model assumption, which means we just rewrite this sum by removing the CI variable and basically saying, well, clicks have only occurred on documents that were observed and relevant. So this sum is not going to be no longer over all documents, but only over documents that were observed, that were examined, and that were also relevant, essentially. That's what we end up with this sum here. And then what we're going to do again is we're just going to plug in the definition of expectation over our examination probabilities. So what's going to happen then is, well, we work out this expectation. You get a formula of the following form. So we again introduce this examination probability like we have done in the previous proof. So now we have this examination probability times rank, but we're also, again, dividing by that same examination probability because that's the definition of our estimator. So you can sort of see where this is going because we're now multiplying and dividing by the same probability. So these two things just cancel each other out. And then what we end up in is the following equation of the following form, which is exactly the definition that we're interested in, as if we were having the true relevance labels that gives us the exact evaluation metric of interest. So again, there's a couple of key points here, is that by dividing by this probability of examination, we are sort of canceling out the effect that user model introduces, that examination probability gets introduced here. But this also assumes that each probability of observance is larger than 0, because obviously you can't divide by 0, right? Mm-hmm. So there's a sort of implicit hidden assumption here that each document must have some small probability of being observed.
Right. So
and then
in that step with the summation, you've basically, so where this probability of observance appears, mm-hmm. You've basically replaced that OI is 1 with that probability, right? So,
yeah, exactly. That's essentially what happens.
Because yeah, it's a summation over all the relevant documents, and you're saying the only thing that matters is, will this document be observed or not? That's the only thing that, because there's no noise. Yes.
Yeah. I hope I didn't go a bit too fast here, but essentially what we're doing here is we're first taking linearity of expectation. So we're basically bringing this sum that we have here out here, and then it's a sum only over things that are observed, and then the expectation, it just becomes the probability of that thing being observed, essentially. Mm-hmm. Yeah. And again, these things cancel each other out, and you very nicely get back the original evaluation metric that we would want to have if we had the true relevance labels. So this is quite a strong statement, actually, because it says that if we plug in this IPS estimator, which only depends on clicks, we're going to get something out of it that says something about the true relevance labels, which is a very, very strong statement. Of course, depending on the fact that our assumptions hold.
Yes, yeah. So because the estimator is unbiased, this means that we have a really large number of clicks. It's going to converge on the true thing that we're trying to estimate, which is this
exactly
delta. Yes.
Yes.
Completely different from what we had before, where this didn't work.
Exactly. Yeah. Before, no matter how many clicks you collect, even infinitely many, you would still get the wrong answer. But here, it's guaranteed to converge eventually to the right answer.
So this formula is for a single interaction, right? Yes.
Yeah. So normally you would do this over many.
Yes. Yeah.
Many more. Yeah.
Many queries. Yes.
Exactly. All right. So
we have shared this. We shared the slides, by the way. If anyone wants to look into detail at these formulas, you can find our slides online.
Right. Yeah. So far, the proof that I've shown you, we made this assumption that there is no click noise. So in other words, that the probability of a document being clicked, given that it's observed and that it's relevant, is just its relevance, which is 1 or 0, right? But actually, the proof that I've just shown you is a bit stronger than that, because it still holds without these assumptions, as long as if one document is more relevant than another document, that's means that the probability of a click should also be larger. So if we have two documents, one's relevant, one's not relevant, the relevant one should have a higher click probability than the non-relevant one, which is a reasonable assumption to make.
Given that they're both observed, right?
Given that they're both observed, yeah, I should make that clear. So given that both were observed, then indeed these click probabilities should infer a sort of relative preference between the two. And you can prove this by proving that relative differences are inferred unbiasedly. So this still holds even under a click noise setting. So that's quite nice. So what we have here essentially is saying, well, even if there's some amount of click noise, as long as there is some preference that users have over relevant and non-relevant documents, we can still use this very strong estimator that tells us something about the true relevance purely from historical interaction data. So that's very nice.
Can you say something about what you mean with a relative difference?
Sure. So a relative difference, as in if we had two documents, one is relevant, one is not relevant, then we should prefer the one that is relevant, essentially. So relatively speaking, the one that's relevant should be preferred over the non-relevant one.
Right. But I mean the equation, right?
Okay. Sure. So what we have here is we again go over this expectation of our IPS estimator of two models, f theta and f theta prime. And what we can show here is that in expectation, if say model f theta is better than model f theta prime, then our estimator will also show this in expectation. So it's relative. So one model is better relatively than a model f theta prime,
right.
Then these two statements are equivalent, essentially.
So with noise, you won't get the exact value, but you will at least know if one is better than the other.
Exactly, yeah. Which is typically what you're interested in. And in most cases, you would say, oh, I have a new ranker. I just want to know if it's better than what we already have in production or what we already have deployed. Then this relative difference is exactly what you're looking for. Yeah,
right.
That's a good point. Yeah, with that, I will wrap up the counterfactual evaluation part. So what basically, to summarize, what we've seen here is that we can do evaluation. So we can say, take some new ranker, f theta, and we just want to know how well does this ranker work. And do that purely based on historical interaction data, historical clicks, and without having access to annotated relevance judgment. So we don't know the true relevance label. And we've shown that under some assumptions of a user model, etc., we can still get a very powerful estimator that tells us this. Right, so in the next part, Harrie, you will take over to discuss how can we use this same type of principle, but for counterfactual learning to rank.
All right, thank you very much. Let's see if I can take over. Yep.
Yep.
All right, indeed, so we've seen how evaluation works, but now I want to take the next step and actually do some learning here. The main idea here is that we're going to take that inverse propensity score that we've just seen, this estimator, and we're going to try and optimize it. We're going to try and optimize our model, f theta, to maximize the value of our estimate. So basically, we have an unbiased estimate. We can sort of estimate what the performance is, and now our goal is to get the best estimate of performance. Like what model gives us the highest estimated performance? And we immediately run into two problems that you see very common in learning to rank, which is this estimator is not differentiable. And we talked a little bit about this in the first part, but we have a rank function here, and rank functions are never really differentiable because they're not soft, right? You're either at rank 1 or 2, you can't be somewhere in between, so we have sort of this discreteness problem. But there have been some solutions in counterfactual learning to rank field that I'll discuss with you now. The first one, which comes from, I think, the first counterfactual learning to rank paper, is based on this idea of upper bounding the rank function. So in rank SVM, which is this very old Pairwise method from 2002, Torsten Joachims already showed that we can have a differentiable upper bound on the ranking function. So if we have our function, so the rank for a document D, according to our model f theta and in the document set D, so after it is sorted all the documents in D, we can rewrite that as a sum over all the documents in D or in the ranking. And then we're going to add 1 for every document that has a, let me say this right, has a greater or equal score than your document. So the intuition here is if a document has a greater score, it's in front of you, so your rank must be 1 higher than that one. If you have an equal score, we're going to assume the same happens. You have an equal score with yourself, so you always have rank 1. So it's basically you're counting, you know, this document has 3 documents in front of it, it must be on a rank 4. That's basically what's happening here. That still doesn't help us because this still isn't a differentiable function. It's equal to the rank. But you can quite easily say that you can do sort of use a hinge loss to create an upper bound, which is the following. again, we're going to rank over all these documents, but now we're going to take a maximum operation. So we're going to take either 0 or 1 minus the score difference between two documents. And we're going to sum over that. So if these scores are the same, if this other document has the same score as the document that we're getting the rank for, we will get 0 here, which means that we get 1 out of this operation. So if you have the same score, it counts as 1. If the score of this other document is higher, you'll get a score greater than 1. If it's lower, you'll get a score lower than 1, but never less than 0 because of this max operation. So if you work this out, you can quite easily see that this score will always be greater than the rank. So we're going to call it rank with an upper bar, just to indicate that it's an upper bound on the ranking. There are other choices. So there's a sigmoid-like bound. This is famous in lambda rank or lambda mart, even the latest lambda loss. It's the same idea. We have a function here that uses the score difference between the document that we want to rank of and all the other documents, which is always greater than the indicator function we have up here. So if we sum over it, we'll have some function that's greater than the rank. The nice thing is that these are all differentiable. So while we can't directly optimize rank with something like stochastic gradient descent, we can optimize these functions. And because these functions are an upper bound, if we minimize the rank, the upper bound on the rank, we're indirectly minimizing the rank, right? We know the rank will always be lower, which is what we're trying to do.
Right. Can I ask, so if you have this rank bar, this differentiable upper bound, and you would use this in evaluation, you would essentially overestimate the rank typically, right? Mm-hmm. You would.
Yes. Yeah. There, you would. Yeah. You wouldn't use this for evaluation because you don't have this problem, right? In evaluation, you're just trying to estimate the performance.
Right.
This is really just for optimization purposes.
Right.
Because, I mean, in reality, the score difference doesn't matter. The user is just going to see a ranking, and it doesn't know what scores cause that ranking. So we don't need anything that depends on the scores. But when you do optimization, you need something like that, right? You need these scores to become closer to each other.
Exactly.
Otherwise, they're never going to change rank. So, yeah, this only makes sense if you're doing optimization, if you're learning. All right, so we've seen the average relevance position metric before, or ARP, and we saw that it just used the rank of a document, right? It's basically the average rank of every relevant document, as you can see over here. So we already have immediately have a upper bound on an IPS estimator for this specific metric, right? So if we so instead of using the lambda function here, we plug in the ARP function, which is just the identity. So we just get the rank here. So this is going to estimate the ARP metric based on clicks, as Rolf discussed before. But now if we want to maximize, or actually minimize ARP in this case, we want to minimize the ARP, we want the relevant rank to be as low as possible for all the relevant documents. So optimize our F function for this. We can use this upper bound function by just using that instead of the rank function. And now we have an upper bound. We have a value that's greater than the actual metric. And trying to minimize that value, we expect that it will indirectly minimize the actual ARP. You can do this by stochastic gradient descent if you're, for instance, doing deep learning or find that easier. For linear models, there's also a way of doing it by quadratic programming. And this basically is the rank SVM. It's a very old learning to rank baseline, of course. All right, so that helps us for the ARP metric. But of course, we've seen there's many more metrics that are slightly more complicated. So in 2019, we saw a paper at CIR that extended this approach for additive metrics. So if lambda is a monotonically decreasing function, that basically means if you have x and y is greater or equal than x, if you plug those values into lambda, you'll get a smaller value, right? So y is greater or equal, but lambda y is smaller or equal than lambda x, is the idea. And of course, for a lot of ranking functions in evaluation, it looks like this, right? For DCG, the lower your rank is, or the further down the ranking you are, the less of a score that you receive. So a lot of our IR metrics are actually these based on these monotonically decreasing functions. And we can also quite clearly see that if we have an upper bound on the rank, if we put that upper bound into our lambda function, it will be a lower bound, right? So if we're going to have something that either is the rank or overestimates the rank, it's going to underestimate the discount that is received. So we have a lower bound, right? So for instance, for DCG, discounted cumulative gain, as it's usually used, we can see 1 divided by log 1 plus the rank is always going to be greater or equal than 1 divided by log 1 plus some upper bound of the rank, something that's equal or greater. So if we're trying to maximize DCG, we can maximize this thing over here because it's differentiable, and we'll indirectly maximize this, the actual DCG, usually at least. Right, so if we put this together and we'll plug this into an IPS estimator, for the DCGG, we get an estimator that looks like this, right? So we haven't written out the fraction here. We have to the power of -1 over there to get rid of it so that we can show it in a single line. This is the true thing, the true metric that we're trying to estimate. If we then convert this to our IPS estimator, so again, we're filling in that lambda function that we saw before. We have our unbiased estimate that now looks like this. So again, for every click, we're going to reweigh that by the discount that we get according to the metric, and inversely weigh it with the probability of examination, as Rolf discussed before. But for optimization purposes, we need this to be differentiable. So we just replace this rank function by the upper bound of a ranking function. And now we have something that's always lower. And because we want to maximize these metrics, we can use this to maximize this lower bound and then indirectly maximize the metric. So using this trick, we can, for almost all IR metrics, get a differentiable lower bound on the unbiased estimate.
And the trick is just to upper bound that rank, because that's the only operation there that's
yes.
problematic, right, for computing gradients.
Yes, yeah. This is it's a little different than what we see in traditional learning to rank, and I suspect that we'll see more variation of this. But it just shows that actually you don't. Yeah, it's you can quite an easy trick can actually already solve most of these problems. Yeah, so again, we have something we can optimize with stochastic gradient descent. There's also a more complicated convex-concave procedure. You can read this paper if you want to know more about it. But the main idea is we have a trick here which gives us a bound that's differentiable. All right. I'm going to summarize sort of the approach because we've talked about quite a lot, and we want to make sure that you understand what this actually looks like in practice. We've talked a lot about the theory so far. The first step in this counterfactual approach is you need to have some model of position bias. We need to explicitly sort of have these probabilities because we're going to use them as propensities. Then we acquire a large click log. So you need some clicks that occurred in the past under your ranking system that you already had running. And then for every click in that data set, in that log, you will have to compute the propensity. So using your model of position bias, how likely was a user to examine this document? And then based on that propensity, you can then use the IPS way estimator to calculate the gradient of a bound on that unbiased estimate. So as I've shown before, for ARP, you can upper bound the rank and then reweigh it according to the propensity score, and then update your model by adding or subtracting this gradient. And repeating that process will optimize the unbiased estimate of performance. Now, of course, we didn't show it here, but you want to probably also check on some validation clicks if you're still learning and not overfitting, because overfitting can still happen. But the main idea is here. This is have some position bias, have a large number of clicks, compute this propensity, the probability of examination per click, and then optimize a bound on your unbiased estimate, and repeat that over and over. All right. To show the effect of an unbiased approach versus the naive approach we showed before, we did some experiments for this tutorial, and we follow the standard setup. So these are semi-synthetic experiments where we take an existing learning to rank data set where people have made annotations. So we have judges that told us this is relevant, this is not relevant. And then we simulate queries by sampling from the data set. We create a ranking using some baseline ranker. So we use some simple ranking function that is decent, but not optimal. So we still have room to improve. And then we simulate click noise and position bias based on this ranking that we displayed, where the clicks are based on relevance, but they're noisy as well. And then we can do some hyperparameter tuning also based on these unbiased evaluation methods. So we simulate a large number of clicks. We make sure these clicks are noisy and biased. And then we don't use these annotations anymore. These annotations used to create these clicks, but we can use them to evaluate them. Because in this case, because we are the ones who are simulating these clicks, we know that the annotations really are what's relevant or not. This is, of course, very different from a real scenario because these annotations, well, we discussed the problems earlier. But in a simulation, we can really evaluate our models because we have the ground truth. This is what it looks like. I'll walk you through this. We have on the x-axis the number of training clicks, the number of clicks used to optimize the model. Notice this is a logarithmic scale. So we're going from 1,000 to 100 million. We're using the average relevant position as a metric. So the lower, the better. Because this is a simulation, we know the real user preferences, which you wouldn't know in the real scenario, which means that we can calculate the optimal performance. We call this the oracle. So it's this green line down here. This is if you know what people find relevance, what's the best model that you can create, right? So usually because features aren't that great in these settings, we will not get a relevant precision of 1, but we get one, as you can see, around 11, between 11 and 12. This is if you had this information you normally never had. Our production ranker, the ranker that we use to get our clicks, is over here at rank around 13. This is what we use to get our clicks. So we have a system that is not that bad. It's not horrible, but it's very far from being the optimal ranker, right? There's still a lot of room for improvement. Then this blue line here, that is the naive estimator. So this is the estimator Rolf was discussing before, where you see a click and you don't do any debiasing. You just assume that it's only a noisy indicator. And as we see here, this is clearly biased. So it does improve over the production ranker. So we do see an improvement, but it converges around 100,000 clicks, right? After 100,000 clicks, it doesn't improve, even if we go all the way up to 100 million clicks. And I guess this is what we were trying to say in the discussion before, the very important point. If you're working with a biased method, you can't just increase the number of clicks, right? We have 1,000 times the data and we're not improving anymore because we're converging on the wrong place. This is the IPS estimator. It starts much higher. It has more variance. This is a bias variance trade-off. But as you can see, over time, it actually converges on the optimal ranking. So as we can see, about 100,000 clicks when the naive estimator has converged. Using our IPS estimator, we can still improve and really converge on the optimal performance. So in this case, adding more clicks will bring you to the real point eventually.
Right. And this is, of course, done under a simulation, like you've said, where we made certain assumptions and those assumptions hold. Would we see something similar if we were to run this on real user data? Could we make a similar plot?
Yes, very good question. The answer is no, and the main reason is because we have the real relevance labels here, right? We have that Y function. That's how we can actually calculate the performance here. In the real world, you would never be able to do that, right? You wouldn't be able to say, oh, I'm doing this good. If you were, then you don't need to learn from clicks, right? So we cannot make this plot at all. But it is a very interesting question in that what it would look like, the question, what would you see on the other side, not in a simulator? And it's very hard to say because of this bias, right? If you're going to ask a naive estimator, how is this model over here doing, this naive model? It's going to tell us it's amazing, right? It's doing really good. Because of this policy reinforcing behavior, right? It puts much more weight on these documents that were in high positions during logging, and it doesn't know that's incorrect, right? It doesn't correct for that. So if you're using an estimator and the estimator is biased, the estimator is not going to tell you it's biased. That's the whole point, right? The estimator is going to show you, hey, this is all great, everything's going perfect, we find the optimal ranker, but in reality, that's not what's happening.
Right.
Yeah, this is very good for people who are working with actual user data to realize, I think. Very good takeaway, yes. All right. I think we discussed everything about this plot so far.
Mm-hmm.
Right, so we know now how to correct for position bias. And there's a very obvious next question that Rolf is now going to answer for us, which is, how are we going to find the position bias that we're going to correct for? All right, so I'm going to give you control again. There we go.
All right, should be good.
Yep.
All right, thanks, Harrie. Yeah, so what we've seen so far is counterfactual evaluation, counterfactual learning to rank. But at the core of all of these methods is this component of position bias, these propensity scores or examination probabilities, or however you'd like to call them. So that's what we've seen. We've seen counterfactual evaluation using unbiased estimators, counterfactual learning to rank, which essentially is just optimizing these unbiased estimators. And again, at the core is this propensity score, this probability of observing a specific document in a ranking during data collection. And that thing helps us to remove this bias from user interaction. Of course, the question then becomes, how can we calculate this propensity score? Where does this come from? Can we get a number for this? Because that's really the core of these methods. So what I'm going to talk about here is showing how this propensity score can be estimated, in this case for a specific kind of bias, position bias. There are other types of biases that can happen when you're collecting clicks. So we're going to restrict ourselves for now to position bias, where there's a large amount of research that has already been published on that. but it is an active, ongoing topic of how do you deal with other types of bias. I should say that these are biases that have to do with typically where you display something in a ranking, or whether users observe a particular document, and not necessarily things like societal biases or other stuff like that. It's really specific to this propensity score, this examination probability. So moving on, just to recall what we've said before, position bias is a form of bias where higher positioned results are more likely to be observed and therefore clicked. And this is a very common, reasonable assumption to say that, in, for example, web search, things that are higher ranked are just going to get observed more. That's fairly reasonable. The assumption that we're going to make here is that this observation probability only depends on the rank of a document. So it's only going to depend on whether we've put this document at the top versus, say, at the bottom. This might not be as reasonable of an assumption. It's probably one of the most important factors, arguably, on whether a document gets observed, its position in the ranked list. But there could be other factors that influence this. But for simplicity, we're just going to assume that it only depends on that rank. And then the objective for position bias then becomes estimating for each rank what is this examination probability, this observation probability, or this propensity, essentially. And this was this type of purely based on position user model was first formalized in this paper by Creswell et al. From 2008.
So you already mentioned that you think the assumption is probably I don't want to say incorrect, but
right.
could be incorrect. Right. Is that a problem? Do you think that's a problem?
It might be. It depends a bit on how strong the real behavior violates this assumption. Like if there are some other influences, but by far the strongest one is this purely based on rank position bias, then it's still worth to account for this and model just that, because it simplifies a lot of things. It really depends on how users behave. Right. I think for a domain like web search, this is a reasonable assumption to make. For other domains, maybe not. It really depends.
You're saying it might not be exactly that, but the model doesn't need to be 100%.
Right, it doesn't have to be purely exactly right.
Okay.
Yeah.
Yes.
So moving on, what I'm going to show you here is one algorithm for estimating exactly this. So given a rank of a document, what is the observation probability? That's what we're interested in right now. So that's basically for each rank, one probability. So this is one algorithm called the randomized top n results. In this case, we're going to have, say, 4 results: document D1, D2, D3, and D4, here indicated with different colors. So the point of this algorithm is that when you are going to collect clicks, or even before then, you could run this, you're just going to randomly shuffle these top n results. So we might get a different ranked list that we show to a different user that looks like this: document D3, D4, D1, D2. Right? So they're in just a uniformly randomly shuffled order. And then we do the same thing, and then we keep collecting a large amount of user interactions where we constantly just randomly shuffle the order in which these documents appear. If we average this over many, many user interactions, what we're going to end up with is that document 1, say the blue document, has been placed at rank 1, say 25% of the time, and in rank 2, 25% of the time, etc. Right? And each document, in fact, appears at each rank with an equal amount of probability. So that means that when you collect a large amount of clicks, the relevance of each individual document is no longer a factor in determining whether users click on the particular rank. So the fact that a user would click on rank 1 versus rank 2 is no longer affected by the fact that maybe there was a more relevant document at rank 1 because the same documents were shown at each rank. So the only factor that can influence whether there was a click on rank 1 versus rank 2 is now the actual position of that rank. So the position is exactly the thing that we want to measure. So you can just run this on, say, a large amount of data. Even before you start collecting clicks, you can just run this randomization process. And this gives you some estimate of how many clicks we expect to see at rank 1, rank 2, rank 3, rank 4, irrespective of what document we put there.
You're saying if you have a large number of queries, you've shown this ranking a lot of times. Each time because it's just randomly shuffled, the average relevance per rank is the same, so
exactly.
it won't have any effect. Yeah.
Exactly.
On average, yes. Yeah.
Yes. So that's the key approach here. And then what we can get out of this is, of course, that maybe relative to rank 1, rank 2 is clicked maybe half as many times. So what this tells us is a sort of relative observation probability. How often is rank 2 seen or observed relative to, say, rank 1, etc. It doesn't actually tell you the exact observation probability, because a user could type in a query and never even look at it, of course, not get any clicks. It's always relative, essentially. So to formalize this a bit more, this algorithm, it's fairly simple. You just randomly shuffle the top n items, you record clicks, and you aggregate clicks per rank, and this will give you, say, a certain amount of clicks for rank 1, rank 2, etc. And then we normalize this to obtain these propensities, the probability per rank of it being observed. Here again, I will state we only need propensities that are proportional to the true observation probability for doing learning. So when we're interested in learning, we just want to know a propensity that is proportional to that true observation probability, because the true observation probability is fairly hard to measure. And during learning, typically what you would do, for example, if you would use stochastic gradient descent, you would set a learning rate, you would tune that in any case. So the magnitude by which you scale these probabilities, as long as it's still proportional per rank, should not matter. That's sort of the intuition behind that.
If I understand you correctly, that means that you don't need to know that a document at rank 1 has a 90% chance of being observed. You just need to know a document at rank 2 is half as likely to be observed than the one at rank 1.
Exactly.
Right?
Yeah, exactly.
And I guess if you estimate them all twice as high, it doesn't matter, because it's the relative differences stay the same.
Right. Yeah. And if you recall the learning that we do when you take one of these estimators and you divide it by this propensity score, for a stochastic gradient descent algorithm, again, if all these propensities are all multiplied by 2, that's basically saying I'm going to multiply all my samples that I'm learning from by 2, which should not matter.
Yeah.
Right. So obviously this is not ideal. So why is it not ideal? Because we are randomizing the top n results, and that may negatively impact users during this data logging. So if we're going to just randomly shuffle results, users may not like that. There are certain expectations that users have of systems, and randomly shuffling is typically not very ideal.
Putting it very mildly.
Yes, it's very bad, typically. So there has been research into looking into methods that minimize the impact on the user, but still being able to infer these position bias parameters. So this first one is called rand pair, or random pairs, where you choose one rank in your ranking and you randomly swap one other document in your ranking with the document at this pivot rank. And what this will give you is it will give you the relative propensities, the relative examination probability between the 2 ranks that you've swapped. Using this, you can actually then, by the chain rule, figure out all the other relative probabilities, the observation probabilities. So you can get the same thing as the randomizedly shuffling the whole top n results by just swapping pairs, which is obviously much less invasive than randomizing the whole top n results.
So this would be like what you're saying is you would take, for instance, document 1 and 2, and then sometimes show them in one order, and sometimes you put 2 and 1 and 1 and 2,
exactly, yeah.
or you put them on their own place.
Yeah.
And then at some point you would know something like 2 has half the chance of being observed. Yeah.
Exactly, as 1, yeah.
Okay.
Yeah, and then you typically choose like one pivot rank, say rank 3, and then you swap rank 1 and 3, or rank 4 and 3, or rank 6 and 3, but you keep that pivot rank the same. Yeah. Another interesting way to minimize the impact on users, but still being able to estimate this position bias, is something called interventional sets. And this is a really interesting idea that tries to exploit the inherent sort of randomness in data that comes from having actually multiple rankers in production. So if you are a web search engine, or you have some other user-facing product, you're probably going to be running A/B tests anyway. That's an industry standard that's commonly done. And you're typically going to run more than one A/B test. You're going to run many A/B tests, hopefully. So these A/B tests are essentially random interventions. You're showing a ranking to a user, maybe in set A, but in your test B, you might show a different ranker. So you're sort of doing a shuffling or some sort of random changes, and you're assigning users to these different rankers. And the idea there is, can we exploit sort of this inherent randomness that is in that collected data, because we are deploying multiple rankers to random subsets of users. And this is interventional sets. So to go a bit more into detail on that, we have seen that we can measure position bias very straightforwardly by performing randomization, just shuffling these top n results or shuffling a pair of results. Again, we want to avoid randomizing because that negatively affects user experience. So again, the main idea, use these sort of many randomized interventions that are already taking place because of A/B tests. And there are several papers about this fairly recently that go more into detail on this idea. To show you how this works, here we have a small illustration where we have two rankers, ranker A and ranker B, and there's an A/B test going on that the company decides to do. And it happens to be the case that users are 50-50 assigned to these two rankers, and that ranker A and ranker B, the difference is that they swap document 1 and document 3. That just happens to be the case. What we can get out of this data is we can observe that on rank 1, we've seen documents 1 and 3, and on rank 3, we've also seen documents 1 and 3. So we can say something about the relative position bias between document 1 or between rank 1 and rank 3, similar to how we would do this sort of random pair experiment in the same vein. The problem here is that we cannot say anything about essentially document 2 or document 4 because that intervention simply didn't take place. The idea is that if you have sufficiently many A/B tests, then also for rank 2 and rank 4, we'll eventually get some amount of data that can help us infer the relative preferences there. So to show you that, here is a different scenario where we have, say, an A/B/C test, where we have, say, a 33% assignment of users to A, to B, and to C. And what we see here is that for rank 1, we see documents 1, 2, and 3 appear an equal amount of time. For rank 2, it's just documents 2 and 1, where document 2 appeared more frequently than document 1 because of this 2/3, 1/3 assignments that happens there. So this data is slightly different than the uniformly randomizing your top n results, in the sense that some ranks have certain documents that appear much more frequently than other ranks. But you can account for this because you can measure how often you put certain documents in certain ranks. So you know, for example, that on this rank 2, that document 2 was shown 66% of the time. And then we can still use these probabilities to infer relative examination probabilities. So we can say something about rank 1 and rank 3 and rank 4 because of this yellow document 3 that appears in all 3 of them. But we have to be careful to account for the fact that there's a slight distribution mismatch that is not uniformly random. So there's an extra probability that you have to account for in intervention harvesting.
So this, from a practical sense, it sounds like you're saying if you're doing A/B tests, you're kind of already doing randomization experiments without knowing it, right? You're already swapping ranks. And so that data you can sort of simulate as if you were doing those experiments or get similar outcome, but you have to correct for these different distributions. And
exactly,
so
yeah. So you have to be a bit more careful, where in the previous approach, you would just, you have uniformly random assignments, so you can just calculate exactly almost immediately just by aggregating. Here you have to be a bit more careful. But other than that, yeah, that data is practically free if you're already running A/B tests. So this is a very practical tool that practitioners of learning to rank systems can use to already get a sense of what kind of position bias is happening, how strong is that position bias, and then eventually using that for counterfactual learning to rank.
Nice, yeah. You've gone from randomize everything and who knows what happens to user experience to maybe you already have this day data lying around.
Exactly.
Nice.
Yeah. So moving on to the, so what we've seen here so far is how do we estimate this position bias? What we have also seen is, so we've seen how to estimate this position bias, and we've seen how can we learn given that we know what the position bias parameters are. So we've seen this counterfactual learning to rank, which depends on knowing what that propensity score is, and we've seen a way to estimate that propensity score essentially. So the idea here, this is also a recent line of work, is to jointly learn and estimate these things together. And so what we have seen, right? Counterfactual evaluation with unbiased estimators, counterfactual learning to rank by optimizing these unbiased estimators, and then estimating these propensity scores that you need for these approaches through either randomization or intervention harvesting. And so far, we have really treated these things as two separate tasks, right? Two separate problems that need to be solved, learning and estimation of position bias. But recent work has explored what if we do that together in one single model. So the idea here is that we go back to our previous assumption, our user model, our user examination model, where we had our click probability of a document being clicked, given that it's observed, or being clicked and observed, can be decomposed by a relevance probability and an observation probability. So the probability of it being clicked given that it's observed times the probability of it being observed at all. So here what we've said before is that if this observation probability is known, then we can just apply IPS and we can, learn a ranker in an unbiased manner. The idea is to jointly learn and estimate these two things. So this first part, where we learn an optimal ranker given a somewhat correct propensity model, which we've assumed so far, is just the IPS-weighted learning to rank that we've seen before. So we say our probability of relevance, essentially, can be the probability of a click happening, so something in our click log, corrected by this observation probability, our inverse propensity score, if you will. But we can also swap this equation around. We can move this observation probability out and move our relevance probability in. And that's the second step, where we can say, well, given that we have hopefully a good model, a good ranker, can we learn an optimal propensity model? Can we say something about the propensities if we know how good our ranker is, how relevant certain documents are at certain positions? And that's exactly what this type of work tries to do. So tries to solve both of these problems simultaneously in a single model. And typically this is done by alternating between these two steps. So first try to learn an optimal ranker given some propensity model, hopefully a good enough model, and then improve that propensity model given that you have now learned an improved ranker, and sort of iteratively improving both models to eventually converge to something that is hopefully good.
Yeah, that seems a little strange, right? Because you're learning your ranker before you know the position bias, it seems. So it probably will not be optimal, but
right,
maybe better than what you started with. Then you use that ranker to update your observation probabilities, which probably also won't be optimal. And then you'll go back and update your ranker again with your new observation probabilities, what you're saying.
Right.
So can we prove that this leads, this eventually leads to our unbiased estimate that we want?
Right. Under some additional assumptions, I believe that you can prove. The key idea there being that you are always slightly improving your models. That's sort of the key idea. Is that you're continuously improving both your ranker and your observation probability. That you never optimize one at the cost of the other. And then because they're both getting better, eventually your observation probability model should be really good, so that it gives you also a very good ranking model and vice versa. But it's very easy, of course, for this to spin out of control because, right, you might be optimizing under a wrong propensity model, a wrong ranker, and sort of go the opposite way. So you have to likely make some additional assumptions.
I also noticed that you're calling the relevance probability a ranker here, right?
Right, yeah.
But does this, because normally a ranker doesn't have to follow a distribution, right? You can give any score as long as the ordering is correct. Is that still the case here, or does the ranker need to be close to the relevance probabilities?
So if you already know the relevance probabilities, the problem is pretty much solved of learning to rank. So if you have a good model of that, then you're already done. So this approach doesn't help. So you don't necessarily need to have a good idea of this relevance probability if you have a good ranker. I believe the paper does something about this, but I'm not entirely sure, honestly.
All right. Yeah.
Yeah, but that's a good point, though. I mean, if you do know the true relevance probabilities, or have a really good model of that, that's a much stronger statement than having a good ranker, because that's a much harder problem to solve in general. Yeah. So yeah, moving on to just to summarize it. So if you have an accurate model of relevance, you can find an accurate propensity model and vice versa. That's the main idea there. A benefit is that you don't need a randomization there because you're estimating your propensities based on, you're learning them while you're also optimizing your ranking model. And recent work has gone with this approach either via sort of an expectation maximization approach, which is iterating between these two steps in that manner, or a dual learning objective, both recent papers from 2018. Yeah, that pretty much wraps up the estimating for position bias and also how we can learn jointly a learning to rank model together with estimating position bias. We're now going to move on to actually a different kind of bias. So far we have talked largely about just position bias, which is a common assumption that is made in work in this area. But there are obviously other types of biases. So Harrie, you will, I guess, take over for the trust bias part.
So besides position bias, there is other forms of bias, as we mentioned. One of them that's been addressed in the counterfactual learned rank literature is trust bias. Specifically, there was some work from 2019 where they both estimated the effect of this bias, measured it in some way, but also introduced a method that debiases for this bias as well. So trust bias is similar to position bias, but a little bit more trickier, a little more complicated is perhaps a good way of saying it. What happens is that users very often overestimate the relevance of higher ranked documents. In plain language, if a user sees a document at rank 1 on a search engine, usually a search engine that is making a lot of money, they think, well, this search engine must know what they're doing. They're very successful. So if it thinks that this should be the first document, then probably it's right, and probably this document is relevant, even though they might themselves not have guessed that it was relevant. So they will click on this document because they trust the search engine, and they're going to overestimate the relevance because of this trust. And this will happen more on higher ranked documents than on lower ranked documents. So further down the ranking, it's less likely that people think, oh, this is going to be more relevant. In fact, they're going to more likely to underestimate the relevance there. So it's related to position bias because it varies per position, but it's not the same. It's not an examination probability. This is not about observing it. It's about how they perceive the relevance, or how they estimate something being relevant. The way that we're going to model this is we're going to call this y tilde the perceived relevance. So this is the relevance that the user thinks the document is going to have, instead of the actual relevance. So the y that we have before, which is how relevant the user actually thinks the document is. A click is now the probability is modeled by the probability that a user thinks this document is relevant, that the perceived relevance is positive, conditioned on the actual relevance and the ranking, times the probability that it's observed in the ranking. So this still captures our position bias, this part. We still have position bias as we know before, but because of this probability, it's slightly different, right? So this is more about the ratio between correct and incorrect clicks. The way that it's modeled in this paper is by conditioning this click on the actual relevance and on the rank of the document. So for every rank k, there is an epsilon plus parameter, or epsilon k plus. It's a probability that someone will think this document is relevant and just click on it if they observed it, given that it's relevant, right? So it's actually relevant and they will think it's relevant. And epsilon k minus for when they think the document is relevant, but it's actually not relevant. So this is the probability for, or I should say, this is the probability that we have an incorrect click. And this is the probability of having a correct click.
So does this mean that for, if these epsilon values are the same for all k, we would be back at the original position bias model?
Indeed, yes. If it didn't vary per k, it would be the same. Yeah. The problem is that we get more incorrect clicks at the top than at the bottom.
Right.
But if that's no longer the case, then there's no trust bias, right? If the rate is the same at all levels, yes. They introduced this new estimator to correct for this bias. It's called Bayes IPS. And for every click, so here we can see we have the same estimator again. We're summing over all the documents. We're inversely scoring with observation probability for position bias, everything we've seen so far. But now we multiply, we multiply by the probability that this was actually relevant, conditioned on that it was clicked and its position. They make some additional assumptions because we don't know the relevance, but they under the assumption, I think that relevant and irrelevant documents are equally likely. They end up at this weight. So for every click, it's being reweighed according to the position where it occurred. If on that position there are more correct clicks than incorrect clicks, it's weighed more heavily. If there are more incorrect clicks, it will be weighed less heavily. The problem is that these values can't be inferred to randomization experiments. As far as we know, you can't do something like this rand pair that we see, or any of the other methods where we do randomize documents, the ordering of documents, and then estimate these values. So they use EM estimation optimization here, as we also have seen in the previous section. And the trust bias they found is what we see here in these two graphs. So through EM optimization, and these results are actually quite interesting because they tell us also something about how IPS works without this correction for trust bias. So here we have the position. We have 5 documents being displayed. And this is the examination bias. This is the probability that this document is going to be observed. According to the classic model, the just only position bias model that we see in the previous section, and this new trust position bias model, which is both addressing trust bias and position bias. So here we have the only position bias model, and we see that examination bias drops very quickly, right? It goes from 100% to 60% in the next position and continues to drop. The trust bias model gets a very different examination bias. It still drops, but it doesn't drop as heavily. So it still thinks that a lot of these positions are actually still examined, even which is very different from what the other model thinks, right? So it still thinks that these are examined. And the reason it can do this is because it also has the trust bias. So here we have the epsilon plus and the epsilon minus parameters per position. So we see on this axis. And we see these are the epsilon plus, so these are the probabilities of a click if the document's relevant. And according to this model, this drops very slowly. So people are still very likely to click on something if it's relevant, wherever they observe it. Although we do see that there's less clicks further down the ranking. Now, if we look at the incorrect clicks, so the clicks on non-relevant documents, we see that a lot of these occur on the first position, and then we have a very quick, steep drop in this bias. So we expect a lot of incorrect clicks at the start, and then much less. So the effective trust bias seems to be quite strong. All right.
So for the first plot where we see the position bias, we see that for the trust bias model, still think we're examining more at later ranks.
Yes.
But because we are in this trust bias setting, these documents get clicked less when they're irrelevant at these lower ranks because of this trust bias. So in a sense, this traditional position bias model might be sort of the product of these two without properly decomposing it. So the trust bias model is sort of decomposing this thing into properly examination and trustworthiness.
Right, yes, because both models are trying to explain the same difference, but the position bias model can only change the position bias because it's the only parameters it can learn. Exactly. And it's going to capture, right? So both models have to explain why do we see so much fewer clicks on, for instance, position 5. And what the trust bias model says is this is because we see much less clicks on incorrect documents, but we still see roughly the same amount of clicks on correct documents. So that's the trust bias explanation for why there's much fewer clicks. The position bias model can't do this, right? It doesn't have these trust bias parameters. It only has the position bias. So it's going to say, oh, I think it's much less likely that these documents were observed. So it's because they weren't observed that they weren't clicked. So it's different explanations for the same behavior. It appears that the trust bias model captures reality more closely. Like it's better at predicting clicks. It's better at explaining clicks. What's interesting is when you use the trust bias estimator, we don't see very large improvements. Because you might think, looking at these differences, right, these weights look very different. You would expect very different results. That's quite limited. Probably because the position bias model is also correcting a little bit for the trust bias. It's just doing it implicitly. It's doing it by lowering these examination probabilities, which is not the right way, right? It's the same effect. Most of these clicks get less weight, but it's for the wrong reason.
Right, that makes sense.
That could explain what's happening here, of course. There might be other explanations, but it seems very likely. All right, so that's very interesting. And I hope in the future we see more of these different biases examined. Yes.
Okay, so yeah, thanks, Harrie. That was an interesting part. Yeah, different biases, definitely important. In practice, I think most problematic is still the position bias. Has a large impact. And so for what I'm going to do in this section is give some practical considerations if you are a practitioner of a learning to rank system and you want to, actually start using a counterfactual learning to rank method. So one problem that is fairly typical when doing any type of counterfactual analysis, really, but specific to counterfactual learning to rank systems, is this problem of high variance. And this high variance can be caused by many factors. One problem is that you don't have enough training data. Another problem could be that you are suffering from extreme position bias, which in turn results in very small propensity scores because certain documents, the probability that it's being examined is extremely small. Or you could have a large amount of possibly noisy clicks on documents with very small propensity, just due to variance. And the usual suspects in high variance problems is one or a few data points that have such an extremely small propensity score that they overpower the rest of the data set. So what this essentially means is we are going to divide, so what we're doing in counterfactual learning and what we've seen so far with these IPS estimators is that we are dividing by this examination probability, right? This probability. And if this probability is really small, then by dividing by this number that's, say, close to 0, you're blowing up your estimate. You're generating an enormously large number because of that. And that's the problem that's fairly typical here. So these small propensity scores can cause all kinds of problems with your estimator and also during learning with high variance. So a typical solution, and this is fairly effective, is something called propensity clipping. And in propensity clipping, what we are essentially going to do is we're going to say, well, we have these very tiny propensities, but we're just going to pretend they're not that small. We're just going to clip them to make sure they're larger. So we're going to use values that are larger than the actual propensity. So we're just going to bound the propensity, essentially, to prevent any single sample from overpowering the rest of the data set. So here we have a formula that's the clipped IPS estimator, similar to the IPS estimates that we've seen before. We have this lambda-weighted ranking function. We have some clicks that we're weighing this by. But instead of just dividing by this propensity, by this examination probability, we're limiting it by some factor, say tau. And we're choosing the maximum of these two values. So either that probability or some tau that we can then set. And that tau allows us to control how aggressive our propensity clipping is. And what this solution is essentially doing is it is trading off bias for variance. By setting tau, it will introduce some amount of bias, but it can substantially reduce your variance. And because of that, it may be fairly helpful in essentially the problems that I just outlined, like the high variance problems. So you can clearly see if this tau equals 1, then we're always dividing by 1. Because this probability can never be larger, obviously. So you just get basically your naive estimator that we started out with in this part of the tutorial. Conversely, if you set actually tau to 0, you just get your regular IPS estimator back. So you can change this value anywhere in between to range it from the fully biased naive estimator to the fully unbiased IPS estimator, or any point in between. And this is practically fairly useful. So we're going to go back to this image that we've shown you before, this experiment that we ran, where we have the same lines as before. So just to quickly recap, we have this line here at the bottom. We have the number of training clicks on the x-axis, more clicks on a logarithmic scale. We have on the y-axis the average relevant position again, so lower is better. And then we have our oracle line here at the bottom, which is the best possible performance. We have our red line here, the production, the thing that was collecting the clicks. And again, we have this naive line, the naive estimator that converges to the wrong solution because it is biased. And our IPS estimator that we had before, this sort of teal blue line, that given enough clicks does converge to the optimal solution. And then what we've added here is this clipped IPS estimate. So one where we've set a tau to prevent the problems of the high variance that was introduced. And we can definitely compare this purple line with this light blue line here. And we see that especially when you have few amount of training data, it helps to do clipping a lot. And this is also what we would expect, right? Because you have fewer training data, you're probably going to have more variance in that training data. So it helps to do clipping. And then as we get more and more data, the two seem to converge to the same performance. So we're still getting these benefits of an IPS estimator, even though we introduce a small amount of bias. So it's almost like a best of both worlds type solution. You sort of sit in between the biased realm and the unbiased realm, where after careful tuning of this parameter, you can get really good results. All right.
So, but you need to know the value of, you have to set this parameter, right?
Exactly, yeah, and that's typically the difficult part, is knowing what to set this to. Yeah. And that's, yeah, in practice, very, very hard to do. Also, again, because of the previous, this is a simulation, so we can actually tune this parameter to be optimal. But in a practical setting, that's very hard to do because it's hard to evaluate in the first place.
Right. I think so, what we did here, though, was we didn't use a simulation, but we used validation clicks without
validation clicks.
But yeah. It's not. It's a little bit more messy, than we would like to do.
Yeah, it's definitely tricky. Also, if your evaluation or your validation set of clicks is small, then that thing might also be suffering from high variance. Yeah. So you might want to clip that as well, and that will be very problematic to do. So you need to make sure you have a sufficiently large amount of validation data in order to do proper tuning, I'd say. Yeah, that's a good point. Yeah, so that's probably one of the most important practical considerations is be careful of high variance due to numerous reasons. And the typical solution is do clipping. It works fairly well in practice. So I guess moving on, Harrie will take over to compare basically what we've seen now, this counterfactual learning to rank, where we learn from user interactions, to the supervised learning to rank, the more traditional learning to rank.
Yep. All right. In the interest of time, I'm going to try to be a little bit more quick than we have so far. All right, so we've seen supervised learning to rank in the first part. We've now seen counterfactual learning to rank. And this is a good moment to compare these two methods now that we've talked about both. On the supervised side, we see that we need manually annotated labels, and we see there's many problems with them. The most important ones, they're expensive to create, they're impossible in some settings, and they're not necessarily aligned with the actual user preferences. So even if you have them and you learn from them, they might not lead you to the best system. In counterfactual learning to rank, we don't have this problem. We use click logs, so there's large abundance. They're usually very easy to get if you have a search engine. Now, we're academics, so we actually, for us, it's actually very hard. But for most people in industry where they actually have a ranking system, this is really easy to get. And it usually doesn't cost more than you already have running the system. But, and it's a very big but, you have a lot of noise and biases in this data. So we already seen that this supervised method, it's very well studied, but we've seen it's not very doable for a lot of practitioners. So because we can use click logs in counterfactual, it's very attractive to go this route. But you have to deal with this noise and bias. Noise is not that big of a problem. We see if we have large number of clicks, we can average out the effective noise. Not so for biases. For biases, it doesn't matter how many clicks you have, how big your data set is, you won't get rid of the effects. So we've discussed other solutions, mainly with inverse propensity scoring. But we know this is not the end of the story. We've seen a little bit from trust bias. We know there are much more biases going on, and we know their models can be better. So I would expect this is a very active area of research, and we expect a lot more research in this area. All right. That's a brief comparison. We'll do more at the end in part 4. But first I want to talk about some related work, which is click models. So often we get a question from the audience when we give this in person, which is what about click models? Because click models is are a very established branch of information retrieval research, and they're very related to learning from user interactions, right? So for several decades, people have been trying to model the behavior of users, and the main goal for click models is to find the model that best simulates realistic user behavior. In practice, that means, can we predict where people will click in the future? So if you have a really large click log, can you learn a model that can predict where people are going to be clicking? If you can do that, then you would have found a very realistic way to simulate user behavior, and you can probably better understand it. To capture this behavior, right, to get a realistic model, you have to influence you have to capture all the factors that influence interactions, right? So here we again see you have to estimate attractiveness for documents, what we call relevance so far, but also other factors that we call biases, right? So for instance, position bias is one of them, because these will all affect user behavior, so you need to model them if you want to really simulate that behavior. And actually, one of the methods that we discussed so far, which is this EM optimization to measure or estimate position bias, looks very similar to some existing click models work, basically the position biased model. So it's very related, right? And we mostly see click models in bias estimation. To understand why we're not just what is really the difference, so far I've talked about the similarities, we can see where the differences are if we try to use a click model to evaluate, right? So often a click model needs to estimate attractiveness, how likely is someone to click on something if they've observed it. And often they do this using features. So you'll have some learned function, let's call it M, that gives you the probability of something being clicked or not. So this is like basically a relevance function, as we've sort of seen before. In theory, you can use this function for unbiased evaluation, right? So we've learned this probability that we want to know, this unbiased probability. But in practice, this didn't work. So click models for evaluation have never really taken off. I'm not necessarily saying that they can't be used or should never be used, but in practice we see that they're not being used that well. But counterfactual estimation seems to work very well. So what's going on here? The key difference is that click models rely on feature-based models, on features, right? So we need this M, it needs to take document features. But what we've seen so far in counterfactual estimation didn't rely on any features, right? If we look at our IPS estimator, it just relies on, well, we need this propensity, we need to know the rank. Maybe the rank depends on features, but it doesn't have to rely on features per se. But the relevance part all comes from these clicks, right? So we don't have a model that takes features and tries to estimate relevance. We do it based on a frequency estimate. This is a debiased frequency estimate because we need to correct for instance, position bias. And I think this is the crucial difference, because for a click model, you have to have really good features that can really capture relevance. We know this is an incredibly hard problem. We usually don't have the features to do that. But in counterfactual evaluation, you don't need any features. If you have a lot of clicks, you can estimate relevance by debiasing these clicks. Of course, you need to know position bias. So it's, but it seems that estimating position bias is much more easier than estimating relevance based on features, which gives counterfactual evaluation the advantage. All right, so to wrap that up, click models aim to realistically simulate user behavior, and they have to model attractiveness and biases because of that. And you could do feature-based evaluation with it. In contrast, counterfactual learning to rank has a very different goal. Its goal is not to simulate user behavior, but to look at the learning objective, our learning to rank loss function, basically, and consider the effect that position bias and other biases have on this loss function, so that we can learn without being affected by those biases. And in practice, this leads to unbiased frequency-based evaluation and learning, which is much more reliable usually than feature-based evaluation. All right, is that clear?
Yes.
Right. I think I'll give you the chance to conclude the first two parts.
Sure.
Before we move on to the next.
Yeah, so yeah, just to wrap up this part and to conclude, what we have seen is that we want to leverage user interactions, specifically clicks. Doesn't have to be clicks, but generally clicks. User interactions with these rankings are very biased. And that's where this whole idea of counterfactual learning to rank comes into play, is where we can actually correct for this position bias by using this principle of inverse propensity scoring. But there is a but, it requires an explicit user model. So in this case, we've looked at, for example, position bias as being one of the major models that we typically use, where we say this examination probability depends only on the rank of a document. But it enables unbiased learning from historical interaction logs, which is a very powerful thing because historical interaction logs are, for practitioners, widely available, and being able to learn in an unbiased fashion from them is very powerful. So looking forward to the next part of the tutorial, we're going to look at an area called online learning to rank. And this is also a learning to rank method that learns from user interactions. And again, these user interactions are going to be biased and noisy, but the way online learning to rank deals with these biases is different. These algorithms directly interact with users and handle biases through randomization. And then finally, we'll do a sort of comparison where we contrast the counterfactual learning to rank parts with the online learning to rank parts. Yeah, with that, we're going to wrap up this part of the tutorial. So I'm going to move on to online learning to rank next.
All right, let's move on to part 3 of the tutorial, online learning to rank. In this part, we'll do the following. We'll first talk about online evaluation, where we'll compare different rankers through interleaving. Then we'll spend quite a bit of time discussing dueling bandit gradient descent. That views learning to rank as an interactive dueling bandit problem. We'll then consider a recent alternative method, pairwise differentiable gradient descent, that has learning to rank through unbiased pairwise optimization. And we'll wrap up with a comparison of these two methods, dueling bandit and pairwise differentiable gradient descent. We'll look both at the theory and at empirical evidence. Over to you, Rolf.
Thank you, Maarten. All right, so before we get started with the interleaving, I'm first going to talk a little bit about some related work, because we're talking about online learning to rank, which is bandits for ranking. So in the past, ranking has been modeled as a k-armed bandit problem. And these methods are somewhat different from the online learning to rank methods that we'll discuss in more detail in this part. Specifically, these Bandit methods aim to find the optimal ranking for a single given query. So there are several different approaches to this for these ranking Bandit methods. For example, one approach would be using upper confidence bounds. This is very common in Bandit problems, where you would build upper confidence bounds on the relevances for each document for a given query. Other approaches include divide and conquer approaches, where you split documents in groups such that there are high confidence relevance differences between these two groups. And other approaches include, for example, click-through rate estimation per document. This is somewhat similar to counterfactual learning to rank, where you also have to be careful with things like position bias, but there are Bandit methods that try to do this. So the goal of these Bandit algorithms is really, to sum it up, to find an optimal ranking for a single given query. And as a result, these algorithms do not generalize to other queries. That is to say, there is no resulting ranking model that we get out of them that we can apply to new unseen queries. It's really a specific ranking for a specific given query in a given fixed collection of documents. There is an advantage, of course, to this approach. So the rankings that you produce here are not limited by features. You don't have a ranking model. You don't need to express your documents that you put in this ranking model as features, but you instead know exactly for each document where it should be put in the optimal ranking. Of course, a disadvantage by doing this is that you have to start learning from scratch for every new query that occurs. And that's very different from the goal of learning to rank that we have defined in this tutorial, which is to find a ranking model that generalizes well across all user queries. So with that, yeah, so these types of methods, they have this disadvantage that they don't generalize to new queries, but they are still worthwhile and they can be applied, especially in cases where you maybe have few queries that you really want to know the optimal ranking for. That will be a typical use case. So moving on from the ranking bandits, and we've seen how different this is from what we're trying to do in this tutorial, we're going to now go over to online evaluation, which is the next part. So similar to what we did in the counterfactual part of this tutorial, we're going to start with evaluation, which is figuring out how well does a ranker work. And then later on, we're going to tackle the problem of learning to rank. We want to learn the optimal ranking model. So in the previous parts, we've seen that counterfactual evaluation corrects for position bias in historical interaction logs by explicitly modeling these user examination probabilities and then applying techniques like inverse propensity scoring. And we've also seen that one way of getting these user examination probabilities is through randomization, by randomizing what order documents are shown, and then you can infer for each rank what's the examination probability. There are other methods that can be used to directly perform evaluation through randomization. And two of these methods, the first would be A/B testing, which is a very prevalent technique that is used very widely. And another one would be interleaving. And these types of methods try to answer a slightly different question, which is, should a ranker A be preferred over a ranker B? So they try to answer a question of relative preference of two rankers. Instead of directly absolutely saying this ranker has a certain performance in terms of this IR metric. So a quick introduction on A/B testing. Fairly simply, you have two different systems. Say they are rankers, system A and system B. You have a large population of users, and you randomly assign users to either system A or system B. So you use you randomize system exposure to user to measure the differences of these two systems. Now, this is very powerful. This is very widely applicable, far beyond just ranking. You can apply this to many different things. But as a result, it's not specific to rankings. And there might be certain aspects of interactions in rankings that we can use to do more efficient comparisons. So A/B testing might require a lot of interactions before you know that system A is better than system B. And maybe if we exploit certain aspects of interactions in rankings, we can have less interactions to get the same answer: is ranker A better than ranker B? And one of these techniques, one that was invented almost 20 years ago, is interleaving, which the main idea is that you take two rankings for a query, and these come from two different rankers, ranker A and ranker B, and you create a single ranking out of these. You sort of interleave the results of these two rankers together to produce one ranking that you'll actually then show to a user, and from clicks on this ranking, on this interleaved ranking, you can infer some preference signal between these two rankers. So to show you how this works, we're going to go with an example of team draft interleaving. And this is modeled sort of after how you would pick teams in sports. And here we have two rankers, ranker A and ranker B. Ranker A has documents 1, 2, 3, and 4 in that order, and ranker B wants to show documents 2, 5, 1, and 6 in that order. So the first thing that happens in this algorithm is that we flip a coin as to decide whether ranker A or ranker B gets to pick a document first. So let's say we flip a coin and we get ranker B first. At this point, ranker B will select its highest ranked document and insert it into the interleaved ranking as such. So we now have document 2, which is inserted at position 1. This also means that for ranker A, document 2 is no longer available because ranker B picked this document already. So ranker B finishes its turn, and then ranker A gets to pick its highest ranked document at that time, which in this case is document 1, and adds that to the interleaved ranking. This process then continues, so we flip a random coin again. Maybe this time ranker A gets to pick a document. Well, document 2 is already in the interleaved ranking, so it will not pick that. Instead, it will choose document 3 to add to the interleaved ranking. And then ranker B's turn, it will pick document 5, add it to the interleaved ranking, and then this is the end result that we have. So we have an interleaved ranking that goes documents 2, 1, 3, and 5. Now this interleaved ranking can then be shown to a user, and the user might click on certain documents. So the user might decide to click on documents 2, 1, and 3. And from this, we can infer that ranker A may have been better than ranker B. Specifically, we see that ranker A received 2 clicks, while ranker B received only 1 click. So this is just one of many interleaving techniques that can be used to essentially evaluate whether a particular ranking system is better than another ranking system. And the idea here is that you deal with position bias by randomizing the display positions of documents. So we had a randomization process where we chose to flip a coin whether to have ranker B or ranker A first put a document in position 1. And this randomization is, in a sense, limited because we're still trying to get the top document from either ranker A or ranker B in the first position. So there's still some user experience that's maintained. It's not completely random. It's not completely shuffled, essentially. There have been results recently that show that team draft interleaving is, in fact, affected by position bias. And what this means is that if you have 2 rankers, if they are somewhat similar, but still one should be preferred over the other, this method might infer them to be equal in terms of performance, when there should be actually a preference between one of the 2. And there are other interleaving methods, such as probabilistic interleaving or optimized interleaving. Maybe, Harrie, you can give some more detailed explanation on
yes,
on
sure.
these.
Right, yes. So as you can see, I added a footnote to this proven to be unbiased. So what happens in the online evaluation literature is that their definition of unbiasedness is somewhat different than what we've seen in the first part of this tutorial. For instance, what they do usually is they think of specific situations where they know that they want a certain outcome, and then see if that outcome is being met. For instance, if there's only one relevant document and it's ranked higher by one ranker than the other, then in expectation, so you just showed like a single iteration of the algorithm, but usually you repeat it a large number of times, so you have very often flip these coins and have these preferences. They show that if you average all of those preferences, you would end up finding, for instance, the right ranker wins, the one that puts that one relevant document higher, or if all documents are equally relevant, there would be no preference. However, what they haven't proved is that in expectation, this outcome will match some sort of metric or some sort of relevance, which is precisely what counterfactual evaluation is doing, right? We want to really estimate, for instance, the click-through rate. That's not what interleaving does. It doesn't guarantee that you find the right outcome. So it's biased in that sense, but it's unbiased in specific situations for which they've proven it.
All right, that makes sense. Thanks.
All right.
So yeah, moving on. So this interleaving approach has several benefits over more traditional A/B testing. So like most importantly, it requires magnitudes fewer interactions to get a reliable preference of one ranker over another. And unlike counterfactual evaluation, this interleaving is interactive. You need to have a system that is actually producing these interleaved rankings, showing it to users and gathering feedback like that. This makes it not effective on historical data as opposed to counterfactual evaluation, which is still effective on historical interaction data. So this efficiency of requiring less user interactions to get a reliable preference largely comes from the fact that we are displaying the most important documents first. So we're choosing the top ranked documents for either ranker A or ranker B and putting those in the top position in the ranking. And we're also just looking for relative differences, which is often an easier problem than trying to get an absolute number on how well does a ranker perform in terms of an IR metric. So interleaving is a very powerful technique in providing a reliable, efficient, and interactive evaluation methodology. Yeah, with that, I'm going to hand it over to you, Harrie, to talk about dueling bandit gradient descent.
All right, thank you, Rolf. All right, here we are. Yes, so as Rolf just showed us, with interleaving, we have a method of comparing two rankers. This is the intuition behind this dueling bandit gradient descent algorithm is if you have a way of saying that one ranker is better than another ranker, you can use this to find an improvement over your current system. So this method is about a decade old. This was the first time we see online learning to rank, really, where we have an interactive algorithm. And the idea here is that if you have your ranking system, your ranking model, you can sample variations of that model, so models that rank slightly differently. And then you can use interleaving to see if this variation, if ranking this in a slightly different way, leads to an improvement. And by following that sampling models, seeing if there are improvement, the idea is that you estimate the gradient of the model with respect to user satisfaction. So you can do optimization. Here's the algorithm in text. So I'm going to walk you through a visualization after this, but the main idea is for every query, so you start with your model, you wait for a query, after receiving the query, we sample from the unit sphere in a random direction. So in the parameter space, if you imagine the parameters of our model to be a vector, we sample in a random direction there. We take that random direction, move a small step in that direction, so we have slightly different parameters, and that will be our candidate ranking model, which is slightly different than what we have so far in our current system. These two models will give you different rankings, and you can compare them using interleaving. So for that query that you got, you can now show an interleaved ranking. We just saw one way of making such a ranking. And then if the new model wins that comparison, you update your model in that direction. Let's look at that again, but this time with a visualization. Over here we have the user. Here we have our model. Our model has two parameters, two weights, visualized by this vector over here. The user issues us a query. It wants results for this query, of course. But first we're going to look at the unit sphere around the model. So a unit circle, because we're in 2D space, will uniformly sample from this circle. In this case, we have this model, which is slightly different. It has a higher weight in the second dimension. And this results in two different rankings, because these models will score slightly differently. So we expect these rankings to be different as well. We can interleave them using one of the methods we talked about before. So we get a ranking that combines the results of both. We can show this to the user. The user may click on some items, which gives us a preference. So in this case, we see the user seems to prefer the new system, system B, the candidate system. So we want to update our model in that direction. We estimate the gradient to be towards our improved model. The problem here, of course, is that clicks are very noisy. So we're not going to fully commit to this change. We're going to take a very small step. So we're going to slightly update our model in that direction. And over time, you expect it to oscillate in the right direction, right? So a lot of clicks are incorrect, but if you have a lot of clicks and you take small steps, you're slowly going to move towards the optimum. Or at least that's the idea here. Right, so very simple algorithm. Using this intuition of interleaving can give us relative differences. From relative differences, we can do optimization. There was also a theoretical side to this work. So they proved that under certain assumptions, for instance, there's a single optimal set of parameters. There's one optimal model. The space is smooth. So if you make a small change, you don't get radically different rankings. The user experience mostly remains the same from slight changes. They prove a sublinear regret. So the algorithm will eventually approximate the ideal model. And how long this takes depends on a lot of factors, like how many parameters you have, how smooth its space is, etc. But the idea is that we can prove that it should approximate this over time.
So could you explain maybe a bit more of the sublinear regret? What would that mean?
Right, yeah, so this is a term from Bandit literature that we haven't seen so far. Regret is basically every time you take an action, how much the difference between the reward you get for that action and the reward you would get for the optimal action. So it's like the amount of performance that you were missing for that action, and then you add up the regret over many iterations. Like you continuously add how much performance you were missing in the past up to where you are now. If it's sublinear, that means that it's growing not by any linear rate, which means that at every step this difference must become smaller. Otherwise, you would have linear growth. So it means that you must continuously be getting closer by some amount. That's the basic idea here. So it's kind of a proof of convergence, sort of, but it's a little a different look on it. All right. Here's some results from some simulations. We've seen in the first part how we can do these simulations. They're slightly different, but the idea is the same. We again base behavior on these annotations we have in a data set so that we can really measure the performance. And as you can see here, it learns quite quickly initially. So this is a perfect model. We have no noise, no bias here. Impressions is just an issued query. So somebody issued a query and interacted or didn't interact with the ranking. And NECG, the higher the better. And we can see that Dueling Bandit learns very quickly initially and then slowly starts to improve. And does it matter whether you use probabilistic interleaving or team draft interleaving in this setting? The differences are very small. It's more about finding the direction of improvement, not about getting these individual comparisons correct all the time. The informational setting, we have more bias, more noise, and we still see it learns, although it gets stuck earlier. All right, so this method really forms the basis of the fields. This started about 10 years ago, and most work continues here. So one example is this work on reusing historical interactions from 2013, where the idea is we should look at our past interactions, our experience so far, and use that to guide exploration. So instead of doing this unit sphere where we sample in all directions, what if we try to sample from the directions that are most fruitful? Or in the opposite way of putting it, avoid exploring in directions we already know don't work. So avoid sort of trying things you already have proof for that they don't work. What they do is they sample a large set of rankers as a candidate set, so not just one. And then based on an historical click, they simulate an interleaving so that they can compare, make a guess on which of these rankers is better, and then remove the loser from the set until you have one left. So you start with a large number, and then you end up with the one that you think is most likely to win, so that you don't have to try all those directions you already think won't work. This is some results from that paper that introduced it. There's more lines than we need to look at here. These are standard dueling Bandit grain descent. And these two lines up here use candidate preselection. So you can see it really speeds up learning and convergence. It's much quicker and it reaches a much higher point. This is 1,000 queries, and the improvements seem quite big. However, there's a big but here. 1,000 is a very small amount of iterations. In later work, this was run over a much longer period of time. As you can see here, 10,000 queries. And now we see something different. So there's some more methods here that are not important right now. This is standard dueling Bandit grain descent. This red line up here is with candidate preselection. And we can see that up to that 1,000 point, somewhere around here, things look very similar. We see it learns very quickly. It's reached high performance at a very early on. And in the previous plot, this seemed to be converging, but now we see that actually that's not the case. What's happening here is the performance is slowly degrading over time, to the point that it's worse than dueling Bandit grain descent. So an important thing to keep in mind here is we're in the online setting. So we cannot measure the performance, and we can't do something like early stopping. In practice, you wouldn't know when you were at this spot. So it's not that, like you might do in other machine learning settings, you can say, we're going to stop the learning here and continue on. Right, so this also shows that this way of evaluating is very fragile, right? Because from a plot like this, you think you can draw some hard conclusions, but then when you look on the long term, you see something very different. So besides this work, there was also other work that's tried reusing historical interactions. You have some examples cited here. We're not going to discuss these works here because, similar to this work, they don't consider long-term convergence, which means that we might still be in situations where performance drops like this. They also weren't evaluated on the largest available industry data sets. They're often evaluated on very small data sets where results you can get, there's high variance in the results. With random rankers, you can already get very good results, for instance. Which means it's still unclear whether these methods really work and whether we can really reliably reuse historical interactions. We don't exactly know why this performance is dropping, but it seems to be that some bias was introduced. So it seems to be that by limiting exploration, it's reinforcing some incorrect behavior. You can think of it as you think this document should be very high because you showed it there. You receive a click, and now you're going to keep showing it up there, and you're going to discard rankers that put it somewhere else because you've seen the clicks there. But maybe the clicks you saw there were because it was in the first position. Right. So if you use your historical interactions without correcting for position bias, you might be enforcing the wrong idea. Something we saw in the first part of this tutorial. Could explain what's happening here, but this is unstudied, so we're not certain about that. There's another way of another group of methods that improve on dueling Bandit gradient descent called multileave gradient descent. What happened was that at some point multileaving was introduced, which is a variation on interleaving where you evaluate multiple rankers simultaneously. So instead of combining the rankings of 2 rankers, you can combine the rankings of 3 or more rankers. Naturally, you can extend dueling Bandit gradient descent to not just look at one candidate ranker, but look at a large number of it. And this is exactly what multileave gradient descent does. And the idea is if you compare more directions for every interaction, you have a higher chance of finding an improvement. So visually, if you think back on the visualization we had before, it would look something like this. So instead of having one best model and one candidate ranker, we now have 3 of them in this case. So we have 3 additional rankings that we can compare in our interleaving or multileaving. And we can, for instance, find that 2 rankers are better, and we can have an average direction. And this turns out to be much more robust. If we look at the results, we see very large improvements initially, but again, not in the long term. So there's a similar trend here. If you look at these original papers, they look at the first 1,000 impressions mostly, and we can see really big improvements there. But then if we look at the long term, we see the improvements are quite small. This is the perfect setting under noise. We still see a difference. To their credit, this paper did look at the long term improvements as well. So this was not a discovery that was made later. But we see here it's learning faster, but it's not converging at a better place. So we're really speeding up the learning rate, but we're not converging somewhere else. And the main idea here is that this method doesn't limit exploration, but it's doing it more efficiently.
Would the same theoretical guarantees of dueling Bandit gradient descent also hold for multileave gradient descent?
Yes, I think so. I don't think anyone has looked at this, but I think you can take the theory and apply it here as well. Like basically, you could look at multileave gradient descent as doing multiple steps of one dueling Bandit gradient descent.
Right.
But there's nothing published on this, so don't take my word on that.
Okay.
The downside of this approach, though, is that we have really large computational costs. So, because now we're not working with one ranking system, if you want to get the most out of this method, you will be having tens of, maybe 50 ranking systems. So it's nice we can learn quicker, but we have to work harder for it. So this can really lead to practical problems. Speaking of problems, there's been some serious problems discovered with the dueling Bandit approach and all of its extensions. Mainly, if you look at the performance at convergence in a simulation, for instance, in sort of a toy example, we see that the performance at convergence is much worse than we know is possible on the data set, even under ideal user interactions. So here we have a similar graph we saw before. Queries on the y-axis up to 1 million, NECG again. Dueling Bandit gradient descent with a linear and a neural model. And this line up here is if we run lambda mart, so an offline model. This is a simulation, so we know the ground truth relevance. In practice, you would never be able to do this, but here we can calculate the skyline, what's optimally possible. We saw this before where we called it the oracle. And what happens is that we see a really large gap between dueling bandit gradient descent and this oracle method. So what's really possible on a data set. And this is a perfect setting, right? This is this is the ideal user circumstances. There's no noise, there's no position bias. This is really a toy example. And still it's not getting this right, which means that something is really wrong. Another thing that we see here is that if we compare the linear and a neural model, there seems to be no advantage in using a neural model. This goes against a lot that we know from supervised learning to rank. So there's really something wrong here. And this is especially jarring since we have a proven sublinear regret, right? It should continue to improve. One more thing to mention, this data set is called MSLR 10K. It's from the Bing search engine by Microsoft. This 10K stands for 10,000 queries. And we have 1 million issued queries here, which means that this is about 100 epochs. So we have 100 epochs over the data set, which is a really large number for a data set like this. And we still are very far from optimal performance. We have a really big gap. So there's definitely a big problem here.
So does this mean that likely, even if we would go beyond 1 million to 10 million, 100 million, or even further, this line would still not be able to close that gap?
We don't have the definitive answer because the only way to, we don't have theoretical proof that it doesn't. But the only way to find out would be to run this experiment 10 times as long. I don't have the resources to do that. But so it is possible it gets there. It's extremely unlikely. And in practice, I mean, it's still a problem because we still have a method that requires so many iterations that it would never get there in practice. Because this is a situation with no noise and no bias.
Right.
This is a situation with quite some noise and some bias. Not even that much. And you can see it already, it's becoming much slower already. So this is much too slow, right? This is impractically slow.
Exactly.
Yeah, so even if it converges there, by the time it gets there, yeah, it might be the end of the universe. Right. So because of this difference, because this was observed to be quite, we saw this difference between what's possible on a data set and where this method seems to converge is so big. We've looked at the regret of the original paper, which all the other methods build upon. And remember, we had 2 assumptions. The paper makes more, but these 2 are the ones we'll focus on now. There's a single optimal model, and the utility space is smooth. It turns out that these assumptions don't hold for any of the ranking models that were used in practice. So any of the models that we described here, and the metrics that we described here, these assumptions don't hold. So the assumptions don't hold, so the proof doesn't hold either. It's unsound. The only thing we need to prove this is the fact that the utility is scale invariant with respect to our ranking model. Now, what does that mean? That means if we have our utility function, so we saw some metrics before, and we use our ranking model here. So we use our ranking model to calculate the utility. If we take the model and multiply it by any positive number, we will get the same utility, right? When you're sorting documents and you multiply the scores by 2, the ordering is not going to change. They still have the same ordering. The scores are very different, but the ranking doesn't change. So if the ranking doesn't change, the utility is the same because the utility is only based on the ranking. At least for most settings, right? Any practical setting I can think of at least. So the first assumption, there's a single optimal model. It's very easy to show that it isn't the case. At least if you're working with linear models or with neural models, because you can multiply some weights in those models and get the same scores, but multiplied by some constant factor. So we already see, for a really large class of common ranking models, this assumption is never true. I think you can also extend this to tree-based regression. Is that what, was that your question? Or
no, that's all right.
Yes. So the first assumption already doesn't hold. That might not be a big deal, but it shows that something's wrong here. The next one I think is a much bigger deal, the smoothness of the space, which we're really using because we're taking small steps here and we're relying on those small steps to guide us in the right direction. The way that smoothness is defined here is by Lipschitz smoothness. I'm probably pronouncing that wrong. Excuse me for that. The idea here is if you have some constant number, some constant, some real constant, you have your two parameters from your possible parameter space. The difference in utility, so the difference in performance between these two rankers in this case, has to be smaller than if you take the Euclidean distance or some distance between these two parameters vectors times this constant, right? So it means that if you move this, if you take a step in the parameter space, the difference, the size of your step should put a limit on the size of the change that you could be making, right? If a small step should not lead to a very large change in performance. It's very easy to prove that this is never the case if you use this idea of scale invariance. You can actually, so what you see here is we can rewrite these assumptions by playing with scale invariance, and we can show that we have a setting here which is never true. Because you can, basically, you could always pick, you can, for every positive constant, this has to be true, but you can pick this one to be infinitely small. You could, for whatever L you choose, you can pick an alpha for which it is no longer true. So we can prove that this condition is never true, this assumption, for a linear ranking model quite easily. You can do the same for a null ranking model. So we will never have a smooth space for either of those models. Here's a visualization to give you a better understanding. If this is one ranking model, one of these points here, so again, we're in a 2D model space. Every line on this, every point in the same direction of that model is this equivalent model. So all of these models, we're talking about linear rankers here, we're using a linear scoring function. All of these are the same, because this model will just score twice as high, the same scores times 2 as this model over here, etc. So these will all result in the same ranking. Similar for a different model there. You can draw any line actually, and it will, any circle around the origin, and it will contain every ranking model there is. Which means that somewhere here we'll have the best model, for instance, maybe over here, and somewhere we'll have the worst model, maybe this model over here. That means that all of these are equivalent. Same for the best model, which means that near the origin, the distance between a ranker with optimal performance and with the worst possible performance becomes infinitely small. So with any step size, no matter how small, you can go from the best to the worst performance in one iteration. And this goes against the entire idea of dueling Bandit gradient descent, where you slowly improve your performance. Right, so these assumptions don't hold. The proof is unsound, so we don't have a proven regret bound here that's sound. Empirically, we see that these methods don't approach optimal performance. They get stuck somewhere else. And we see neural models have no advantage over linear models. So something is wrong here. These holes in the proof could explain why this is happening, but it could also be that there's even more wrong with the method that we don't know yet. But this is a possible explanation. The question is, how do we move forward, right? We have this method, it doesn't work, but we still want to do online learning to rank. There's two solutions broadly speaking. The first one is we can extend the algorithm. We can think of how do we improve dueling Bandit gradient descent. For instance, maybe we can introduce a model that doesn't have these issues. This is basically the last decade of research. So we've seen 10 years of people trying to improve on by extending dueling Bandit gradient descent. It hasn't led to better points of convergence. So something we did 2 years ago is we thought we need to find a different approach, something that isn't this Bandit idea, and see how that works. Because so much effort has been spent on this dueling Bandit approach, it hasn't led to something we would use in practice. It's probably time to try something very different. What we came up with was pairwise differential gradient descent. The idea here is that we don't want to use this model sampling. We don't want to sample model variations and compare them. So the method dueling Bandit gradient descent has gradient descent in its name, but it looks more like it behaves like an evolutionary approach, where you sample variations and use those variations if they're improvements. It seems much more similar to that than to stochastic gradient descent. Our intuition was we can take a pairwise approach and we can make it unbiased, which leads to a differentiable loss, a differential pairwise loss. And we don't have to use anything of an online evaluation or sampling of models. So we might have something that looks more like what we see in other machine learning fields, where you have a loss function that you can optimize. All right. This turned into pairwise differentiable gradient descent. It's based on a Plackett-Luce ranking model, which is a probabilistic distribution over documents. This means that we have a ranking model as we've seen so far, but during learning, we're going to turn that into a probability distribution. And basically what we're using here is a softmax function, but its older name would be a Plackett-Luce model. We take e to the power of our score so that we get a positive number, and we divide by the sum over e to the power of all the other documents. So this is always a valid ranking, just like you see in any softmax layer. And this gives us the probability that one document is the best document that should be placed next out of the entire document set, according to our parameters. Immediately we have a difference with the previous approaches, is that we now have some level of confidence. This model can say, oh, I'm 70% sure that this document should go next. And this varies depending on the documents that are available. It can vary per query and even within the ranking. For instance, it could say, oh, I'm very clear about the top 3, but not about the top 10. Dueling Bandit didn't have anything like this. There was no notion of confidence there.
Right. Does this also mean that previously we would take our document scores and rank by sorting by these document scores, but since they're now probabilities, we could sample a ranking with high probability being the sorted ranking, but in a probabilistic manner.
Exactly, yes. So during learning, we're going to sample from this ranking, but as you rightly say, if you sort according to the scores, you have the ranking with the highest probability. So it's the maximum likely MLE. No, maybe I'm saying it wrong, but it's the one with the most likelihood. So during learning, you would sample it, but if you don't want to continue that, if you don't like using a sampling method, you can switch back to the actual model when you're done with learning. Right. And then the next question is, how do you optimize this model? Right. We have our probabilistic model. We thought that going the pairwise direction would be very fruitful. So we looked at previous work. So for instance, work all the way from 2002 already uses clicks to infer pairwise document preferences. So in this example, a user clicked on document 3 here. And we're going to assume that that means that this user prefers document 3 over 1 and 2 and 4. This is based on eye tracking studies. people usually go from top to bottom. So if you click on document 3, that most likely means you saw 1 and 2 and didn't think they were good. People often also look one space further, so that's why we include document 4. You don't have to do this if you're uncomfortable with that. Right, so we have these pairwise preferences. When you see a click, all the documents that are in front of above a click document and the first unclicked document is the rule we use. However, we can immediately see that this approach is biased, right? Because some preferences are more likely to be inferred than others due to position bias. So we discussed in the first part, that means it's, in this case, it means the lower you are, the more you have to lose, right? Document 1, for instance, most clicks will just be on document 1 if it's on top, presumably, due to position bias. So document 1 is less likely to be seen as preferred over document 2, just because it's on top. So it's unfair in a way due to position bias. We have to do something here. And the approach we take here is by looking at reversed pair rankings. So a reversed pair ranking is the same ranking as the one that we showed where we received a click, but we swap 2 documents. So in this case, we want to infer that document 3 is better than document 1. But before we look at this preference, we're going to consider the other ranking, where these 2 documents have been swapped and document 1 might have been clicked. The idea is that if document 3 is more preferred than document 1, we would more likely see this click pattern than that click pattern, right? If document 3 is preferred, we would expect this pattern to be less occurrent than that pattern because people will probably click up there instead. If they are equally relevant, then we expect that both of these clicks are equally likely, is the idea. And the idea is, if we show these rankings 50% of the times, we can find a reliable preference between 1 and 3, right? If half of the time we showed this ranking and the other time we showed that ranking, and we only look at clicks at the 3rd position, we would get a very accurate idea of which of these 2 is more relevant. You can think of this as sort of the opposite of what we saw in the swap K strategy when we were estimating position bias. It's kind of the inverse of that because we're trying to estimate relevance here. The big clue here is that we're not going to actually show this 50% of the time, but we're going to score them as if that's happening. So we're going to make sure that we have the same outcome or a similar outcome without actually doing that. And the idea here is that we use the ratio between these 2 rankings, which sort of gives us a bias between these 2 directions in preference. So when we see a click on document I, meaning that it's, and we no click on document J, but in a position where we think it's observed, we want to update according to this preference. As you can see down here, we have this we want to update the document in this direction. I is preferred over J, our distribution, and then therefore our model. But we're going to weigh that gradient with this weight rho. And this weight is basically the probability that you showed the ranking in the other direction divided by both probabilities. So it's a number of between 0 and 1. And the more disadvantaged you are, the more likely it is the closest to 1, right? If 99% of the time you would show the opposite, this would be close to 1. If 1% of the time you would show the opposite direction, this would be close to 0. So you're weighing the directions that are unfairly biased against more heavily to account for this. All right. I'm not going to go into too much detail here because we don't have the time, But we can prove that if the expected gradient here, so if we, the gradient that we'll get from this procedure is some pairwise gradient. So there's something like this, where we have a difference between a pairwise loss between these two documents, as we see in supervised learning to rank, times some weight, which is unique for these two documents. And we can prove that this weight is going to match the user preferences and expectations. So if there's no difference in relevance between these two documents, this weight will be 0 in expectation, and otherwise it will match the direction of relevance here. And we call this unbiased with respect to document pair preferences. This isn't the same definition of unbiased as we see in the counterfactual learning to rank side. Did you want to ask me a question about that?
No. That's,
All right, I thought you unmute. I thought so. This is, yeah, this is not what we've seen before. It's a different form of unbiasedness.
Right. So it's not about specifically the examination bias or position bias, but it's unbiased in the sense that you're going to get the right document pair preference. Is that correct?
Yeah, right. Yes. So the gradient will tell you this document should be in front of this other document. The problem is that the degree by how much you're going to push those two documents isn't affected here. So
right.
As a result, we don't know if it really unbiased the estimates metric, which is very different to what we saw earlier.
Right.
Okay. To reiterate, it's again an online procedure. We wait for a user query, sample a ranking from our Plekit-Loos distribution, display that ranking to the user, look at the clicks from the user, infer document preferences, then update your model according to those preferences, but we're going to estimate a somewhat unbiased gradient. So unbiased with respect to document pair preferences, not necessarily unbiased with respect to a metric. In a visualization, so we have the user on the one side, the document collection on the other side. We'll get a query, then according to our model, we'll have a distribution over this document collection. We can sample a ranking from that, show it to the user. The user may interact with some documents. We'll get some preferences there. And then we're going to look at the reverse pair rankings. We're not showing this to the user. We're just looking at how likely were we to have shown that. What was the probability of these rankings? Because it tells us how much of a bias we have in one direction or the other. And then we can correct for that and get a somewhat unbiased update. If we now put this method in the plots that we saw earlier with dueling Bandit grade descent, we see something very different. So again, here I'm going to focus on the perfect setting where we have 1 million user queries. Here again, we're dueling Bandit methods. Linear neural look pretty much the same. Here was the oracle, but now I have two new lines. So this blue line down here is this pairwise differential gradient descent method with the linear model. And we see it's much faster. It's like, we can't even observe how quickly it gets to this point because the resolution is too small. But it's many factors faster than dueling Bandit gradient descent. And we see it converges at a much better place, but it's still not at the optimal place. If we plug in a neural model, which we can also update because it's differentiable, we can do the exact same thing just with a different model. And we see it learns similarly fast to the linear model, but it continues to learn and it converges near the oracle. So I wouldn't say it converges at the optimal ranking because we don't have enough results to confirm that, but it gets very close. So it's in the same ballpark basically. And this is actually quite a big deal because it's the first time that we see an online learning to rank method solve a toy example, so solve a toy problem in a simulation. That sounds like a small step, right? Solving a toy problem in a simulation should be the easiest thing to do. So it took 10 years, and now for the first time we have an example where this happened. So this was quite important to the field. And it's also the first time we see a neural method do better than a linear method. So this seems to make much more sense than the dueling bandit approach. On the right, we see what happens when you include noise and bias. And we see that the effective noise and bias is much smaller on this pairwise method than on the dueling bandit method. We see it still learns very fast, still converges at a much better place. The difference in where convergence is much smaller, as you can see over here and over here, versus over here and over there. The neural model, it's slower now. It's not close to the optimal performance yet, but we can see it already starts to improve over the linear model. So yes, this seems to indicate that the pairwise gradient descent method is much better than the dueling bandit gradient descent method. But there's more, and Rolf will take over at this point. So I'm going to give you control, and you can continue this comparison of these two methods.
Right. Yeah. So thanks, Harrie. So yeah, I'm going to continue with this empirical comparison of these methods, of these online methods, specifically of this dueling bandit versus this pairwise differentiable gradient descent that Harrie just explained. So there's been a paper published recently that does a very sort of generalized comparison where the simulations are based on large available industry data sets. These are data sets that are coming from big web search engines, and they contain many queries in the order of thousands, many documents per query. And then with these data sets, we can simulate behavior that ranges from perfect user behavior, where there's no noise, there's no bias, which is what we've seen before as well, to the case where it's extremely difficult, where we have a lot of noise, extreme amount of position bias, etc. Now, one thing that's important in these experiments is that the dueling bandit gradient descent method is provided with an oracle instead of doing its interleaving approach. And this is to really understand the maximum potential of this algorithm. Like, what if you had a perfect interleaving method? So what this means is that when the dueling bandit algorithm needs to compare a ranker A and a ranker B, it will magically know which of these rankers is better than the other. And ideally, this would be your perfect interleaving method. In practice, of course, this is not realistic because you would not have access to an oracle like this, but it gives us an idea of sort of an upper bound on what the dueling bandit gradient descent method can obtain, given that it has this perfect interleaving method. So here in this first plot, what we're looking at is just the dueling bandit gradient descent method with different variations of user noise, essentially. So we see this black line at the top, this one here, which is the oracle. That's if the dueling bandit gradient descent method knows exactly, whenever samples are run a model variant, it knows exactly which of these rankers is better. Then we have a perfect line, which goes up like this. And then we have these two other cases, cascading and non-cascading, which have some random noise in them, or a lot of random noise in them. And then for many iterations, we see that the oracle method obviously performs better than the other. And we also see that the noise variants are suffering a lot. And the perfect method, it still has a user setting that results in being able essentially to infer perfect user preferences, but even that does not get close to the oracle. It's still working its way there.
This seems to suggest that if we find a better interleaving method, it could still improve the performance.
Exactly, yeah. If we were to more accurately be able to say whether rankers are different, we could get closer to this black line. And we see that this black line is improving incredibly fast in the early parts of this plot, which is, there seems to be a lot of potential to gain there if you had better interleaving, indeed. So moving on, we have this other plot, which is the pairwise differentiable gradient descent method, where we don't need an oracle in this case because we're not doing these sort of ranker A versus ranker B comparisons. Like Harrie just explained, we have this pairwise differentiable method where we can use the fact that we're sampling from this Plackett-Luce distribution. And here we see that under a perfect user model, we're increasing very fast and we're converging to some level of performance, which seems quite good. But also in the cases where there's a lot of noise, this algorithm seems to do okay. It still doesn't reach the perfect case, of course, but that can be attributed through the noise. It becomes really interesting when we overlay these two plots. So when we get to compare the pairwise differentiable gradient descent with the dueling bandit gradient descent. So that's what we do here. That's what we see. And what's really striking in this plot is that we see that the dueling bandit gradient descent method with an oracle, so this is literally the best possible performance it could have, like really an upper bound on the performance of this algorithm if we had a perfect interleaving, is not as good as the pairwise differentiable gradient descent method under getting back perfect user preferences. There's still some gain to be had when we're talking about noise, but even that is quite interesting because the dueling bandit gradient descent method with perfect user preferences seem to perform similar to the pairwise differentiable gradient descent with a lot of noise. So that's also a very strong point in favor of this pairwise differentiable gradient descent method. And then finally, yeah, we see that under a lot of noise, dueling bandit gradient descent does not perform very well.
This is this seems very clear cut, right? You have one method under near random behavior, extremely random behavior. The worst case scenario, having performance similar to the other method, dueling bandit gradient descent, under highly ideal situations in a sequence setting.
Exactly. This is a very, very strong indication that, you know, it's pairwise differentiable gradient descent is just better to use. Yeah, that's this very strong result from this plot. I believe these results that I've just shown you here is from MSLR 10K, but these things hold for other data sets as well, other in large industry learning to rank data sets. All right. So to wrap that up, to conclude that, we see that even in these ideal settings, the dueling bandit gradient descent algorithm, the classical online learning to rank, is unable to reach this optimal performance and seems to be strongly affected by noise and position bias. Whereas the pairwise differentiable gradient descent is capable of reaching optimal performance in these ideal settings. It is robust to noise and position bias, as we've just seen. It seems to perform very well even with large amounts of noise and position bias. And it considerably outperforms dueling bandit gradient descent in all tested experimental settings that we have available. So that's a very, very strong point in favor of this pairwise differentiable gradient descent method. So moving on, I think I'll hand it over to you, Harrie.
Sure, yeah, let's stay on your slide, though.
Yeah.
We're near the end. Yes, so I talked about the theory before, and a little bit, we talked about all these different methods that all come from dueling bandit gradient descent that form the basis of this online learning to rank field. And we saw that the original theoretical founding, these sublinear regret bounds that were proven for this family of methods, are unsound for the ranking problems as were usually applied. So all the follow-up work, everything in practice, was done in situations where these bounds don't hold, these assumptions don't hold, so the proof is unsound. So we're missing a theoretical basis there. We saw that the single update steps are as unbiased as its interleaving method. So when you have a single click and you're comparing two rankers, that only depends on the interleaving method you're using. So there's some form of debiasing there, but the entire process isn't provenly unbiased. And as we saw empirically, it seems to converge places that are not optimal in toy problems. The differential pairwise-based approach, the other one we showed, there are no regret bounds here. This hasn't been proven yet. But the single update steps, when we have a single click, we can prove something about pairwise document preferences. But this isn't a very strong form of unbiasedness. It's not as strong as we would like to have it. But it's something. So in terms of theory, we don't really see a advantage in either approach for ranking problems as we see them. So theoretically, there's not much happening.
But given the empirical comparisons that we've just seen, it seems that
yes,
the differentiable approach is quite powerful. Do you think there could be theory that could be proven there that could also give it a theoretical advantage?
Are you asking me, could we prove some regret bounds for
Could we prove a regret bound? Yeah, essentially. Or is there something inherently difficult about that method that makes that hard?
You would have to make more assumptions for sure.
Okay.
But I doubt it. I doubt it though. Yes.
All right. Okay.
But could you go to the next slide? Because we have, so your question leads straight into what about, what, we've seen the state of the field now, what is sort of the future for this? And clearly, as you already pointed, the theory here is inadequate, right? We need to evaluate the theory of this field. A lot of the basis has already been gone. We need something new to get a theoretical grasp on what's happening here and why some of these methods don't work as well. The Dueling Bandit approach appears to be very lacking for optimizing ranking systems. We have a lot of evidence that shows that this is really an inoptimal way of doing things, and it seems these methods should be avoided if you have alternatives. We've seen one alternative, that's this pairwise differential gradient descent. To the best of my knowledge, this is the only alternative. And we saw it immediately performs much better than Dueling Bandit gradient descent. I don't think that this is the end. I don't think that the pairwise differential gradient descent is the ultimate online learning to rank method. But it does show us that trying a different approach has a really high potential. So perhaps this is the way we should go. Perhaps there should be more alternatives here, because if this alternative can do so well, who knows what the next alternative can do. So I expect that the research there has the most potential. Right, so let's end this part with a comparison with supervised learning to rank that we saw at the start, before in the next part we do a comparison with counterfactual learning to rank. What we saw in supervised learning to rank is that we were working with manually annotated labels, and we discussed the problems there, that these are very hard to obtain, and there's a lot of problems with them. For online learning to rank, we've seen that you can learn from direct interaction. So you do your randomization, and based on the way that you randomize the ranking, you can do some debiasing. So these algorithms are interactive. They decide what to display and how to learn from the way people interact with what you displayed. It turns out these methods are very ineffective when applied to historical data. We didn't discuss that here, but there's some work on that that shows that, you can't use this on clicks in the past like you can for counterfactual learning to rank. In terms of bias, these methods are, there's some debiasing, but they're not guaranteed to optimize ranking metrics in an unbiased way. So this is an open problem. An online method that can do this would be amazing, but it's not what we have right now. So compared to supervised learning to rank, it has some advantages. You don't need those labels, but then we don't really know whether we're going to optimize the ranking metrics. So there isn't a clear preference here per se. It's very complicated. All right, and I think that brings us to the end of this part.
All right, let's move on to the final part, part 4, the conclusion. In this part, we'll cover a number of issues. We'll look at empirical comparison of the methods, the many methods that we've seen so far. We'll then summarize the methods from a theoretical point of view, and then we'll take a step back. We'll conclude, and we'll discuss a number of interesting directions for future research in unbiased learning to rank. Over to you, Rolf.
Thank you. Let me share my screen.
You have to stop sharing, Maarten. Yes.
Yes. All right, perfect. So yeah, I'm going to be talking a bit about the empirical comparison of these two methodologies that we have discussed so far in this tutorial. So both the counterfactual and the online part. So far, there has been a single empirical comparison of these two methodologies that was presented at SIGIR last year. So in this work, we use a simulated setup that is very common in unbiased learning to rank, and we apply it both to the inverse propensity scoring methods that we presented in the counterfactual learning to rank part of this tutorial, and we'll apply it also to the pairwise differentiable gradient descent method that we presented in the online learning to rank part of this tutorial. And then in this work, we examine the effects of several different factors on these two different methodologies. And some of the factors that we analyze here are, for example, the number of interactions, the degree of interaction noise, so how many clicks happen on relevant versus non-relevant documents, the degree of position bias, so what happens when there's a lot more extreme position bias, and also the presence of something we call item selection bias, which is a type of bias where we assume there are no clicks beyond rank 10, which is a common thing that happens in web search where people look at the top 10 results but neglect to go to like the second, third, fourth page of the result list. So in this work, we look at basically these two families of methods and compare them. And that's what we've done in these plots, for example. So what we're seeing here is that we have the number of sessions on the x-axis, which range from 0 to 1 million. And on the y-axis, we have the NDCG at 10, which is a typical web metric for IR. The NDCG, the higher, the better. So what we're observing here is several different lines. The gray line is the production deployment ranker, the thing that was collecting the data, collecting the clicks. Then we have this blue and green lines. Those are the counterfactual methods, two different variants. And this orange line, which is the online learning to rank method, the pairwise differentiable gradient descent. And in these two plots, what we are comparing is the effect of item selection bias. So what happens when people stop browsing the ranked list after rank 10, essentially. And just to remind you, this is a user simulation, so we can exactly control for this. And what we see happen here is that the effect of item selection bias is much greater on the counterfactual method than on the online method. In other words, the online method is better capable of dealing with this phenomena of item selection bias than the counterfactual methods are. And we see that because the orange line here converges to a higher result, pretty much on par when there is no selection bias, whereas the counterfactual methods decrease their conversion performance.
Rolf, so is the number of sessions the same as the number of queries?
Not necessarily. So a single query can be repeated multiple times across these sessions. For this experiment, I guess the number of queries is in the couple of thousand, and the number of sessions is much larger. So the same query will repeat multiple times.
Right, but maybe I should say number of issued queries. Like one session is one query.
Right, there's one query, and there could be multiple clicks in that session.
Right. Okay.
Yes, correct. All right, so moving on. So in this next part, we also compared interaction noise. So in the tutorial so far, we've seen that for example, the counterfactual methods, the results still hold even if there is interaction noise. So the theoretical results hold. Here in this comparison, what we are actually seeing is that the counterfactual methods suffer a lot when there is a lot of interaction noise. So on the left, we have very little interaction noise, and on the right, we have a lot of interaction noise, almost random clicks happening here. And we see that the online method, the orange line here, is much more capable of reaching a higher level of performance than the counterfactual methods, even when there is a lot of noise. So we see that interaction noise has a substantial effect on the counterfactual method. All right. So moving on to conclude sort of this empirical comparison where we try out these different methods in a simulation, we see that counterfactual learning to rank produces a slightly higher performance when there is no item selection bias, when there is little interaction noise, but it seems to be very effective if there is a lot of interaction noise. Online learning to rank, on the other hand, is more reliable. It has better performance across many different settings. It handles item selection bias very well, and it's more robust against noise than the counterfactual methods. Overall, these results suggest that online learning to rank is more reliable than counterfactual learning to rank in these simulations that we've run.
So, Rolf, can I ask a quick question?
Yes.
And so these the advantage from online learning to rank seems to come from from the last experiments that you reported on, high interaction noise. How realistic are these high levels of interaction noise? Does it actually happen? Because this was a simulation, right?
And that's a good question, yeah. So what we've done, going back to the slide with near random, this near random noise is indeed maybe not very realistic, because non-relevant documents get clicked 45% of the time and relevant documents only 55% of the time. I'd argue that it depends heavily on the setting that you're in when you're doing ranking. So for web search, I imagine there might not be this level of random noise, but maybe in a different setting, maybe in, like, say, music recommendation, there might be a lot more random noise because of clicks, because users may need to explore more. So I'd say it depends on what setting you're in, whether these results are realistic or not. Yeah.
Thanks.
All right. Yeah, with that, I'll pass it over to you, Harrie.
All right, thank you. There we are. Right, so now we've seen an empirical comparison of these two methodologies. We're going to summarize, or I'm going to summarize the theoretical part of what we've seen so far. We started with counterfactual learning to rank in the second part, where we saw that these methods explicitly model position bias. There is an explicit model of bias in these propensity scores. They're proven to be unbiased in that we can prove that they unbiasedly estimate or optimize ranking metrics, of course under the assumption that we have a correct model for position bias. They can be applied interactively, but they're also applicable to historical interactions. Then, in the next part, we saw online learning to rank. These methods don't have an explicit user model. They use randomization to deal with biases. However, there's no proof that these things optimize actual ranking metrics. We don't have any theoretical proof that suggests that any of these methods are really optimizing any ranking metric. As you saw in the empirical results, however, it seems to be happening though, but we can't prove it. There is some things we can prove. So for pairwise differentiable gradient descent, we saw that we can prove it gets these pairwise document preferences, right? But this is not the same as optimizing a ranking metric. Another thing that we know from these methods is they're only really effective when applied interactively. When you apply them to historical interactions, there are some cases, some exceptional cases, where you can apply something like pairwise differential gradient descent to historical interactions. It seems to be not very effective. So it appears that you really have to apply these methods in an interactive manner. Now, if you put them next to each other, you can clearly see that the counterfactual learning to rank seems to have all the advantageous properties. It can be both interactive or be applied to historical interactions. We can prove it unbiasedly optimized ranking metrics. The only downside is that you need this model of bias, really. Yes, so it seems to be very one-sided on the counterfactual side. Very interestingly, the opposite of what we saw in the empirical comparison. Yes.
Quick question, Harrie, thanks.
Mm-hmm.
And so, how bad does it get if you choose the wrong model for your bias. In a sense, how strong is your theory,
Yes,
and how much does it buy you if you're way off with choosing your model?
How accurate does this need to be? This is indeed not something that we discussed in this tutorial. There is some work. Some of the first counterfactual learning to rank papers did experiments where they correct for a slightly different model than the model that actually was used to simulate data. And it seems to be quite robust. Another thing that we observe is you don't have to, if you have a perfect position bias model, of course it's great. It's going to really unbias the estimate. But if your model is somewhat accurate, it's still better than a model that's even less accurate. Which means if you're not correcting, it's worse than if you're correcting, but you're not exactly right. So that seems to be very robust, but this is not something we can really theoretically analyze, of course, because we don't know what the real biases are. But in practice, it's what we see. Thanks for the question. All right, and with that, I give it back to you, Maarten.
All right, so let's take another step backward and try and formulate some conclusions and then look forward. So we started out by observing that supervised approaches to learning to rank are limited. Annotations often disagree with user preferences. That was one of the key factors why we thought we should look at alternative ways of learning ranking models. We ended up discussing user interactions as a way of solving this problem, but nothing comes for free. User interactions bring noise, they bring bias. We then discussed different ways of dealing with the bias. So counterfactual approaches, they allow for unbiased learning to rank by if you can learn an accurate user model, then you can adjust for the bias, and you then only use a randomization to infer that user model. Online approaches, they allow for unbiased and responsive learning to rank because they can immediately adapt to user behavior, and they can perform randomization at each step, although in a limited way, of course, as we've seen. And then finally, in the last couple of minutes, we've looked at an empirical side-by-side comparison of online versus counterfactual, and a theoretical side-by-side comparison of the two. And we saw that online methods appear to be more reliable from an empirical point of view, and counterfactual methods seem to have all the theoretical advantages. Okay, now, what if we look forward? Well, an important direction and an important paradigm to keep in mind when looking forward in the context of learning to rank would be reinforcement learning to rank. And just to remind you, what was reinforcement learning? Well, if you go back to the original source, or one of the original sources, reinforcement learning is learning what to do. In our case, that could be learning which items to show, which result pages to generate, which rankings to create, learning what to do, so how to map situations, user requests, user profiles to actions, so as to maximize a numerical reward signal. We don't tell the learner what actions to take, what rankings to produce, what result pages to generate. The learner must discover this by taking actions and then discovering which of these actions produce the highest rewards. In the most interesting and challenging cases, these actions may not just affect the immediate reward, but also the next situation, and hence also all the rewards that would come after that. So this is a quote from one of the classical textbooks in reinforcement learning, the Sutton and Bartow book, and I've interjected some contextualization for this tutorial. Now, in contrast with supervised learning, in reinforcement learning, we consider both short and long-term rewards. And the rewards of the actions have to be discovered by trying these actions.
So if I understand you correctly, if we could make a comparison with what we've seen so far, in learning from user interactions, we're also trying to discover how good these actions are, right? How good documents and rankings are. So I can see that's very similar. It seems that what's being added here is sort of the looking at the long-term reward. Is it the right way of looking at it?
I think it is. I think it is, and so that seems promising. This optimizing for long-term effects across queries, across recommendations, across different contexts. And you can think of creating the problem of creating a single ranking as a planning problem. And different constraints, different desiderata may play a role there. Now the ranking, you might want it to be diverse. Yeah, so you may want to think about complex layouts, not a typical ranked list where that's scanned from top to bottom, where the best items should be placed at the start of the list, but maybe there are alternatives. Maybe you have a grid presentation, or you have a presentation where it's important, for instance, on very small screens on mobile devices. Ideally, the very best document is at position 2 or 3, because that's where people on many mobile devices look first. So that is a planning problem, because you cannot just walk down a ranked list or a list sorted by score. Now you have to think about what actions you need to take later, and they maybe hold off on placing the best possible item right now. And another additional constraint might be fairness. Fairness, for instance, if your ranking documents, ranking results in a marketplace where the results might come from different suppliers, you want to keep your ecosystem healthy. You want your different suppliers to benefit from the results that you show. If you only show the most popular or the cheapest result, then this will likely hurt a lot of suppliers, and hence, at the end of the day, in the long run, hurt the health of your ecosystem. Now, interestingly, ranking comes with challenges that make reinforcement learning hard, and one of them is the fact that we have a massive action space. If you think of a ranked list as an action, and then for any somewhat reasonable document collection, we have a gigantic action space. Also, for effective reinforcement learning, what we would need is large amounts of data. And one way of collecting this would be to do a lot of exploration, to let the reinforcement learner do a lot of exploration, but this exploration may hurt the user experience. It might hurt them enough for the users to stay away. Now, in this space of reinforcement learning to rank, there's some existing work. Most of it appears to be theoretical. I don't think any of us know about work that applies reinforcement learning to ranking in practice. Work that does apply it in practice that we know of is in the recommender system space. And to avoid this risky initial exploration phase that I just mentioned on the previous slide, that applied work in the recommendation system space often uses off-policy learning. And that's a very active area of research. You can also see some papers, new contributions at this conference. Let's move on. So future directions, as you saw in the brief summaries that both Rolf and Harrie gave a couple of minutes ago on online versus counterfactual, there seems to be a big dichotomy, a big trade-off, and that actually stimulates a lot of research and a lot of challenging questions on how we could actually get the best of both worlds, the empirical advantages plus the theoretical guarantees. So we'd like to have the robustness of online methods and the theoretical properties of the counterfactual methodologies that we talked about. How can we do this? One avenue that you can think of is maybe we should consider explicit user models and at the same time use randomization during learning. Other future directions, unbiased learning to rank, we believe has lots of unexplored directions. So we've talked about unbiased learning to rank mostly in the search setting, but you can think of recommender systems. You can also think of unusual device settings, for instance, unbiased learning to rank on mobile devices, unbiased learning to rank in settings where a lot of the interaction is voice-based. What is bias? What is noise? How do we correct for bias and noise in those cases? And so far, we've discussed a number of types of bias. There are a lot more that you can think of. Some of them are very technical in nature, in origin, position bias, presentation bias, selection bias. Others are perhaps a bit more societal in nature. Social biases, how do we recognize these biases if they're in data that we've collected, and how do we correct for those types of bias? And that has both an algorithmic aspect and, of course, more of a value aspect. What are desirable metrics to optimize for in those types of correction? And where does this play a role? Well, maybe less obviously so in ranking documents, but certainly it will play a role if you do ranking problems in the setting of HR, human resources. So ranking people for vacancies, ranking vacancies for people, ranking people to form teams to collaborate on challenging problems. That's where these social biases will certainly be in the data, in annotated data, but also in historical interaction data. And the question is how to recognize this and how to correct for it. Some other future directions, as I said, think of different environments, different devices that come potentially with different signals, not just clicks, but dwell time, conversions, purchases, watch time, scroll time, view time, etc. Then another area would be those non-traditional displays that we briefly mentioned a few slides ago. Right, not maybe the most important position is not the top of the list, but somewhere further down the list. Or maybe we don't have a list, we have a grid. And then beyond relevance, how do we optimize for other aspects than just relevance? Diversity, fairness, freshness, how do we optimize for longer term goals, as is the case with reinforcement learning. And then this final theme that that is gaining more and more attention in the community, this theme of responsible ranking methods, responsible learning to rank methods. How can we make sure that our algorithms guarantee a certain level of fairness, a certain level of absence of bias for different user groups during exploration, during learning, after we've collected data, and how should we explain what it is that that we learn during exploration, or that we learn from historical data, and both in terms of what data points were influential for a current decision, but also what would be ways of modifying that decision, maybe by intervening in the data or in the data collection, should we not be happy with the current decision. All right, that's a lot. There are many directions to go for based on our tutorial. We hope you learned something, you enjoyed it. We certainly enjoyed giving it, and as we said at the start of the tutorial, if you have questions, please reach out on Twitter with our handles and with the hashtag LTR tutorial, and then we'll collect the questions. We'll try and answer them on the spot, and we'll also collect them in a video that we'll share with you. Thanks very much.
Thank you, Maarten. Thank you, Rolf.
Thanks.
Thank you, guys.
And everyone else.